Black holes emerge from the mathematics of Einstein's general theory of relativity, where mass and energy bend the fabric of space-time. When mass is compressed beyond a critical threshold, gravity overwhelms all other forces, forming a singularity, a point of infinite density cloaked behind an event horizon. To an outside observer, anything crossing the event horizon vanishes from view, its information seemingly lost. The black hole's presence can only be inferred from the behavior of nearby matter. Stars orbiting invisible centers, high-energy X-rays emitted as gas spirals inward and heats up, or, more recently, gravitational waves rippling through space-time when black holes collide. Their masses range from a few times that of the Sun to perhaps 100 solar masses. Despite their relatively small size, many are only a few dozen kilometers across, their gravitational pull is so intense that they compress that mass into a volume smaller than a city. With hundreds or thousands of solar masses, they may form through the merging of smaller black holes or from the direct collapse of massive primordial clouds. Though difficult to detect, they may bridge the gap between stellar mass black holes and their more massive cousins. These giants dominate their surroundings, anchoring galaxies and powering some of the most energetic phenomena in the universe. When fed by infalling gas, they become active galactic nuclei or quasars, emitting dazzling jets and intense radiation as matter funnels toward the event horizon. Despite their size, their formation remains a mystery. Did they grow from smaller black holes? Did they form directly in the early universe? The answers remain hidden, like the event horizon itself. Unlike electromagnetic radiation, gravitational waves pass through matter unimpeded, allowing scientists to observe phenomena invisible to telescopes. The image, a glowing ring surrounding a dark core, came from the supermassive black hole at the center of the galaxy M87. It confirmed theoretical predictions and offered visual proof of the event horizon's existence. According to general relativity, all matter and energy is crushed into this infinitesimal point. But quantum mechanics, which governs the behavior of particles on small scales, resists such a conclusion. These two pillars of physics, relativity and quantum theory, clash in the realm of the black hole, exposing the limits of our current understanding. When matter falls into a black hole, is the information it carries destroyed? Quantum mechanics insists that information must be preserved, while the classical view of black holes suggests it vanishes. Stephen Hawking's famous work in the 1970s proposed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation leads to the gradual evaporation of black holes over immense timescales. But if the black hole disappears, what happens to the information? Is it lost forever, or somehow encoded in the radiation? Others suggest that information might be preserved in subtle correlations within Hawking radiation, or even escape through hypothetical wormholes. From the outside, the object appears to slow and fade, frozen just above the horizon due to gravitational time dilation. This strange interplay of perspectives raises questions about the nature of time itself. While no evidence supports these ideas, they emerge naturally from the equations and hint at deeper truths yet to be uncovered. Such ideas dwell in the realm of speculation, but they stem from the same mathematical frameworks that successfully predict gravitational waves and black hole images. They warp our understanding, demanding new theories, new tools, and new ideas. Is the black hole truly a dead end or a gateway? If the mass is great enough, no force can halt the collapse. The star implodes, releasing a final outburst, a supernova that scatters its outer layers across the galaxy. What remains is a singularity, A black hole formed not in silence, but in one of the most violent processes known to astrophysics. And yet, from that chaos emerges one of the quietest entities in space, utterly dark, utterly still. Before that point, matter often forms an accretion disk, a swirling spiral of gas and dust heated to millions of degrees, radiating X-rays and gamma rays detectable from Earth. In galactic centers, supermassive black holes orchestrate the flow of gas and stars, shaping the formation and structure of galaxies. Yet, even the most efficient accretion models struggle to explain how some quasars, powered by supermassive black holes, shone brightly less than 1 billion years after the Big Bang. This suggests that black hole formation and growth may be more complex or more exotic than previously imagined. These were the first stars to form after the Big Bang, massive, short-lived, and composed almost entirely of hydrogen and helium. If they collapsed into black holes, they might have seeded the early universe with the first compact objects, laying the foundation for galactic evolution. Detecting their faint traces remains one of the great challenges in observational cosmology. Hypothetical primordial black holes could have formed from fluctuations in the density of the early universe moments after the Big Bang. If such objects exist, they could account for a portion of dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Searches for these primordial relics continue through microlensing surveys, gamma-ray background studies, and gravitational wave observations. The no-hair theorem posits that black holes are remarkably simple, described entirely by just 3 observable properties: mass, electric charge, and angular momentum. Regardless of what falls in, a star, a planet, or a cloud of gas, the resulting black hole is indistinguishable from any other with the same mass, charge, and spin. This simplicity belies the complexity of the processes that form them and adds to the mystery of how information is preserved or erased. In this region, it is possible, in theory, to extract energy from the black hole through a process known as the Penrose mechanism. Though no practical method exists today to do this, the concept fuels speculation about future technologies or naturally occurring phenomena that might tap into such energy reservoirs. Within this swirling boundary, shaped like a flattened sphere around the equator of a rotating black hole, space itself is dragged in the direction of the black hole's spin. This effect, known as frame dragging, emerges directly from the equations of general relativity. In such a region, no object can remain stationary relative to the distant stars. Everything is compelled to move, as if caught in a whirlpool in the fabric of space-time. This seemingly magical energy gain arises not from perpetual motion, but from the conversion of the black hole's rotational energy into kinetic motion. Though largely a thought experiment, it illustrates the counterintuitive and often surprising outcomes of general relativity when applied to extreme environments. In the vacuum of space, quantum fields constantly produce pairs of virtual particles, one particle and one antiparticle, that typically annihilate each other almost instantly. Near the event horizon, however, one of these particles may fall in, while the other escapes, becoming real. From an external viewpoint, the black hole seems to emit radiation. Over vast periods of time, this emission causes the black hole to lose mass and eventually to evaporate entirely. Its implications ripple across disciplines, prompting revisions to long-held ideas about entropy, information, and the ultimate fate of matter in the universe. This discovery by physicists Jacob Bekenstein and Stephen Hawking led to the development of black hole thermodynamics, which formulates analogs to the laws of thermodynamics in the context of black holes. It also gave rise to the holographic principle, The idea that all the information within a volume of space can be encoded on its boundary. Originally developed as a theoretical solution to the black hole information paradox, this principle has since found broader application in string theory and quantum gravity research. Mathematically, white holes emerge as time-reverse solutions to the same equations that describe black holes. Yet they appear to be forbidden by the arrow of time and the second law of thermodynamics. No evidence for their existence has been found, and they remain purely theoretical. Some physicists have speculated that a black hole might be connected to a white hole through a wormhole or Einstein-Rosen bridge, forming a shortcut through space-time. If such structures exist, they could in theory connect distant regions of the universe, or even link one universe to another. However, the stability of such wormholes remains doubtful. Most models require forms of exotic matter with negative energy density to hold the passage open, something not known to exist in the natural universe. The collision produced a black hole over 140 times the mass of the Sun, the first confirmed detection in the elusive intermediate mass range. Such observations are reshaping our understanding of how black holes grow and interact in dense stellar environments. Were they born from isolated stars? Did they form in clusters? Do they spin in aligned or random directions? The data is still sparse, but it accumulates steadily, and with each detection, the hidden history of these objects becomes clearer. These powerful engines regulate star formation through feedback mechanisms, jets and winds that inject energy into surrounding gas, preventing it from cooling and collapsing into new stars. Without this regulation, simulations show galaxies would grow too fast and too large. Black holes, though small compared to the galaxies they inhabit, act as cosmic thermostats, fine-tuning the growth of structure on grand scales. This suggests a deep, possibly causal link between black hole activity and galactic development, though the precise nature of this relationship remains under investigation. In simulations, supermassive black holes emerge not as isolated anomalies, but as integral nodes in the network of cosmic evolution. Another is to investigate the entanglement structure of space-time itself, positing that space may emerge from patterns of quantum information. These are radical ideas, but they arise naturally from the attempt to reconcile black hole behavior with quantum principles. These objects, unanchored and unaccompanied, are nearly impossible to detect, unless they happen to pass in front of a background star, briefly bending its light through gravitational lensing. Such lensing events can reveal the presence of otherwise invisible masses, and have already been used to detect isolated black holes drifting through the Milky Way. While black holes themselves are not a favored dark matter candidate, primordial black holes, if they exist, could still play a role, especially in certain mass ranges currently being investigated. High-resolution models now include sophisticated feedback mechanisms, tracking how jets and winds from active black holes heat and expel gas, quenching star formation. These simulations reveal that black holes can profoundly alter the evolutionary path of a galaxy, determining whether it becomes a sprawling spiral or a compact elliptical. The gravitational potential wells created by early black holes could have drawn in gas, catalyzing the formation of the first galaxies. In this view, black holes are not just the endpoints of stellar death, but the architects of cosmic structure, shaping the universe from its earliest epochs. For an outside observer, an object falling toward the horizon appears to freeze in place, its light redshifted and dimmed. For the infalling object, however, time continues normally until it is eventually torn apart by tidal forces, a process known as spaghettification. For a supermassive black hole, however, the gradient is gentler and an object might pass the event horizon without immediate destruction, only to meet its end deeper within. This distinction raises interesting questions about what an observer might experience while crossing the horizon, and whether any meaningful measurement could be made during the descent. Some models propose a Planck star, a highly compressed core where quantum gravity resists collapse. Others envision black holes as wormholes whose interiors loop back into the universe or emerge elsewhere. In this view, black holes could act as repositories of entanglement, their surfaces reflecting deeper informational connections across the universe. In the darkness of the event horizon lies not only the end of light, but the edge of knowledge, a boundary as profound as the one etched in space-time. For an outside observer, nothing can emerge, no signal, no particle, no piece of information. And yet, this apparent simplicity conceals an ocean of complexity. In quantum mechanics, information cannot be destroyed. The evolution of a system is reversible in principle. A contradiction was born between general relativity's determinism and quantum theory's unitarity. This is the black hole information paradox, a mystery that has driven decades of theoretical exploration. In the case of black holes, the idea suggests that all the information swallowed by a black hole is stored at the event horizon, not erased. The surface area, rather than the volume, becomes the key to understanding information content. In certain models, black holes can be described using lower dimensional strings and branes, and their entropy matches that predicted by black hole thermodynamics. This compatibility is seen as a promising sign, though it remains abstract and removed from experimental verification. These hypothetical low-energy quantum excitations may exist at the event horizon, subtly encoding the information of what fell in. Rather than being smooth and featureless, the surface of a black hole might be imprinted with faint quantum traces, clues perhaps to the history of everything it has absorbed. Whether these hairs are accessible or recoverable in any meaningful way remains uncertain, but they provide one more possibility for reconciling the paradox. This idea preserves information in a highly scrambled form, perhaps beyond our ability to reconstruct, but not beyond the laws of physics. Still, physicists seek analogs in the laboratory, creating synthetic event horizons in systems of superfluid helium, optical fibers, or Bose-Einstein condensates. These analog systems can mimic aspects of black hole behavior, including horizon formation and radiation emission, offering a glimpse into processes that occur in otherwise unreachable realms. Recent efforts to map the shadows of black holes have expanded beyond M87 to include the supermassive black hole at the center of our own galaxy, Sagittarius AI Cos. Though smaller and more variable, Sagittarius AI offers a nearby target for detailed study. The event horizon. Telescopes' images of this object have further confirmed the predictions of general relativity, and ongoing observations promise to refine our understanding of accretion dynamics, magnetic fields, and plasma flows near the horizon. Could a future civilization, armed with sufficient technology and knowledge of quantum gravity, extract information from a black hole? Could they reverse the process of evaporation or reassemble the encoded history of a fallen star? These questions dwell at the boundary between science and speculation, but they are rooted in real physics. As stars burn out and galaxies fade, what remains are these dark monuments, silent, cold, slowly evaporating over trillions of eons. The so-called black hole era of cosmology may stretch across unimaginably long durations, with only the faint hiss of Hawking radiation marking the passage of time. Eventually, even the largest black holes will vanish, leaving behind an empty, flat universe, a final equilibrium state devoid of structure. Some models suggest that as black holes evaporate, they leave behind stable remnants, Planck-scale objects that no longer emit radiation. These remnants could store the final bits of information, acting as cosmic time capsules. Alternatively, the last stages of evaporation could trigger a quantum explosion, releasing the stored information in a final burst. At present, no consensus exists. The truth remains hidden behind the veil of quantum gravity, a theory not yet complete. In them, the known laws of nature reach their breaking point, forcing us to ask deeper questions and to seek new answers. They are places where knowledge fades into conjecture, where every new discovery raises deeper questions. Their presence reshapes not only galaxies, but the minds that contemplate them. Gravitational wave detectors listen to the final moments of black hole mergers, capturing echoes from space-time itself. Each of these tools provides a new window, a different way of seeing the same mystery. These simulations reveal the warped geometry of space-time around merging black holes, the gravitational recoil that can eject the resulting object from a galaxy, and the subtle patterns of waves that radiate outward. They help bridge the gap between abstract theory and observable signal. These rare events produce luminous flares of X-rays and ultraviolet light as the stellar debris spirals inward. Such disruptions can be used to probe the population of dormant black holes in otherwise quiet galaxies, illuminating the demographics of these hidden giants. Jets of relativistic particles launched from the poles of accreting black holes stretch across hundreds of thousands of light years. These jets deposit energy into the intergalactic medium, altering the temperature and density of the cosmic web. The origin and stability of these jets depend on magnetic fields, spin, and the detailed structure of the inner accretion disk, an interplay of forces still being explored. But some reveal themselves through interactions with nearby stars or through microlensing events that briefly magnify background starlight. A complete census of these objects remains a goal of future surveys. Did they form from early mergers or from the collapse of enormous primordial structures? Their very existence challenges models of black hole growth, forcing theorists to rethink the timeline of cosmic history. These tools will allow us to detect lower frequency gravitational waves, track the evolution of black hole binaries, and probe the population of black holes in the early universe. The study of these objects is no longer confined to isolated phenomena, but is becoming a central thread in the story of cosmic evolution. Not a void, but a concentration, not an absence, but a limit, a place where our current understanding ends and the next chapter of physics begins. Whether viewed through the lens of mathematics, observation, or imagination, black holes stand as one of the universe's most enduring riddles. And so the journey continues, deeper into the gravity wells of space and into the questions they inspire. Though popularized in science fiction, these ideas are grounded in legitimate solutions to Einstein's equations. Without this, any such tunnel would collapse before anything could pass through it. These ideas remain speculative, yet their mathematical foundations continue to be explored, particularly in the context of quantum gravity and higher dimensional theories. Some models, such as loop quantum gravity, propose that the collapse might be halted at a finite density, creating a bounce. This could allow the black hole to transform into a white hole, expelling its contents into another region of the universe, or even into a new baby universe entirely disconnected from our own. The constants of nature in that newborn universe could differ from those in ours, potentially giving rise to a multiverse, a vast collection of universes, each with its own physical laws. The birth rate of such universes would depend on the formation of black holes, leading some theorists to speculate that our own universe may be fine-tuned to produce black holes efficiently. In this view, black holes are not only the endpoints of cosmic evolution, but also the engines of cosmic reproduction. This theoretical approach could extract energy from the spin of a black hole using carefully arranged orbits and particle interactions. More speculative still is the idea of a black hole Dyson sphere, a shell of material designed to capture the emitted Hawking radiation of an evaporating black hole for energy harvesting. While no evidence supports such a claim, it raises interesting questions. Could a sufficiently advanced species manipulate space-time to induce black hole formation? Could such constructs serve as computational engines, storage devices, or timekeeping mechanisms? Could the interiors of black holes be altered or engineered to stabilize wormholes or to host entirely novel forms of existence? The mathematics of general relativity places no hard limit on such ideas, though the practical obstacles remain immense. One such star, known as S2, passes close enough to the black hole for its light to be measurably red-shifted by gravity, confirming predictions of general relativity with exquisite accuracy. Any observed anomaly, any unexpected wobble, precession, or shift could signal the influence of dark matter, a modification of gravity, or new forces altogether. In this way, black holes are becoming not just tests of known theories, but probes of what lies beyond. Their brightness fluctuates over days, weeks, or years, revealing the turbulent flow of gas into the event horizon. Some exhibit periodic behavior, hinting at the presence of binary black holes locked in mutual orbit. These systems, while difficult to resolve directly, offer a glimpse of the mergers that shape the galactic core. The ripples produced by their in-spiral and collision carry information not only about their masses and spins, but about the nature of gravity itself. With each detection, the catalog of known black holes grows, enabling statistical studies of their population, formation channels, and evolution. Hypothetical phenomena such as boson clouds, clouds of ultralight particles surrounding black holes, could produce gravitational wave signals unlike any yet observed. If detected, these signals would point to new particles beyond the standard model of physics, perhaps even offering clues to the nature of dark matter. Their very presence continues to challenge and refine our scientific worldview. They embody extremes of mass, of gravity, of energy, and of mystery. They point toward something deeper, a synthesis yet to be found. Any successful theory of quantum gravity must account for black holes and must explain their thermodynamics, their entropy, and their evaporation. In this view, gravity is not fundamental but a product of entanglement, and black holes are complex networks of quantum links. These ideas are still in development, but they signal a shift in how we understand the fabric of reality. Gravitational wave observatories listen for the final cries of merging black holes. Together, these tools are building a composite picture, still incomplete but increasingly detailed. They are real objects governed by knowable laws, embedded in the structure of the universe. Each observation will place new constraints on theory, refine our models, and perhaps point toward deeper truths. They touch on the nature of existence, of identity, of causality. But we are also reminded that progress comes from asking, from measuring, from modeling, from imagining. And so we return again and again to the edge of the event horizon to look outward into the stars and inward into the equations, waiting for the next wave, the next signal, the next glimpse of what lies beyond. The traditional model of black hole growth by accretion, gradually feeding on gas and stars, is too slow to account for the earliest quasars observed in the young universe. Some of these quasars, shining brightly less than 1 billion years after the Big Bang, must host black holes already containing over 1 billion solar masses. One idea involves the direct collapse of massive gas clouds in the early universe, bypassing the intermediate phase of star formation. These so-called direct collapse black holes could begin life with masses tens of thousands of times that of the Sun, giving them a head start in the race to grow. Other models involve dense stellar clusters collapsing under their own gravity, or successive mergers of smaller black holes in highly populated environments. Spectral lines, redshifts, and light curves may eventually help identify the first luminous objects powered by accretion, and by comparing their properties to theoretical models, we may one day reconstruct the story of the first black holes. These giants are found in the brightest cluster galaxies, where cosmic filaments converge and vast reservoirs of gas are available. Despite their size, these black holes can remain surprisingly quiescent, emitting little radiation unless disturbed by infalling matter. In radio galaxies and quasars, jets of charged particles stream out from the vicinity of the event horizon at near light speeds. These jets, aligned with the black hole's rotational axis, are collimated by magnetic fields and can extend far beyond the host galaxy. Their origins remain a subject of study, requiring an understanding of magnetohydrodynamics in curved space-time and the interaction between spinning black holes and surrounding plasmas. A rapidly spinning black hole can, in principle, convert infalling matter into radiation with much higher efficiency than a non-rotating one. This efficiency governs how brightly accreting black holes shine and how much energy they return to their environment. By modeling the X-ray spectrum and variability, astronomers can estimate how close matter orbits before plunging in, and thus derive constraints on spin. These measurements, though indirect, provide valuable insights into black hole dynamics and evolution. These simulations predict structures such as magnetically arrested disks, where strong fields can choke accretion and launch powerful jets. They also produce synthetic images, which can be compared with real data from the Event Horizon Telescope to test our understanding of the near horizon region. The ring-like structure, consistent with theoretical predictions, was shaped by light bending in extreme gravity. More recent observations of Sagittarius A, though more variable due to its smaller size and faster dynamics, similarly align with expectations. These images do more than confirm general relativity. They reveal the structure of spacetime itself, allowing us to see, for the first time, the silhouette of a black hole. These measurements provide constraints on alternative theories of gravity, and any discrepancy might point toward new physics. If these echoes exist, they might carry signatures of the microstructure of spacetime, offering a potential observational probe of the most fundamental layer of reality. Their study encompasses many disciplines, from high-energy astrophysics to particle physics, from quantum field theory to information science. These systems include fluids, optical fibers, and Bose-Einstein condensates. In these environments, researchers have observed phenomena akin to Hawking radiation, albeit in controlled human-scale experiments. Though they do not replicate every aspect of a true black hole, they allow physicists to explore the mathematical structure of horizons, to study entanglement and thermal radiation, and to test hypotheses that would be otherwise untestable. Some researchers have proposed that the structure of space-time itself is best understood through the language of quantum information, with black holes serving as nodes in a vast, entangled network. Though based on a specific mathematical setting, this correspondence has allowed physicists to model black hole thermodynamics, evaporation, and information retention in a controlled theoretical framework. While it does not yet describe our own universe in full, it offers profound hints at the unification of gravity and quantum theory. Their information paradox has inspired new ideas about data storage, entropy, and computational complexity. Some theorists speculate that the internal workings of a black hole might resemble a quantum computer, processing, scrambling, and eventually releasing information. The implications of such a model remain speculative, but intriguing. Future gravitational wave detectors, both ground-based and space-based, will observe the universe in unprecedented detail. They will detect the slow in-spiral of massive black hole binaries, the residual gravitational wave background, and perhaps even signals from the early universe itself. From low-mass stellar remnants to the titanic anchors of galaxy clusters, the full population of black holes is gradually coming into focus. They are both the ends of stars and the beginning of new understanding. And in doing so, they push the boundaries of human thought, drawing us ever deeper into the heart of the unknown. Interactions between stars and the black hole can lead to remarkable events, some predictable, others surprising. The resulting flare of energy, visible across the electromagnetic spectrum, reveals critical details about the black hole's mass, spin, and feeding habits. TDEs serve as rare glimpses into the moment when matter crosses the point of no return, allowing astronomers to study the violent dynamics of extreme gravity in real time. In otherwise quiet galaxies, a TDE may be the only visible sign of a central black hole's presence. By studying the light curves, spectra, and timing of these disruptions, astronomers can infer the nature of the black hole and the fate of the disrupted star. Some flares fade quickly, others linger for years, depending on how much material remains in orbit and how efficiently it accretes. Observations of such binaries have revealed many key insights, including how black holes siphon material from companions, how they emit X-rays, and how their orbits evolve over time. Since LIGO's first detection in 2015, dozens of black hole mergers have been recorded, each one enriching our understanding of mass distribution, formation channels, and the behavior of gravity under extreme conditions. If the kick is strong enough, the black hole may be ejected from its host galaxy altogether, becoming a rogue wanderer in intergalactic space. This phenomenon, while difficult to observe directly, is predicted by simulations and may explain some anomalies in galaxy formation and central black hole placement. By analyzing the mass and spin of merging black holes, astronomers can investigate whether they were formed from isolated stellar collapse or through dynamic interactions in dense star clusters. Patterns in mass ratios, orbital eccentricity, and alignment provide subtle clues to their origins. As the catalog of events grows, these patterns become statistically significant, revealing the diversity and history of black hole systems. This feedback regulates galaxy growth, helping to explain observed relationships between black hole mass and galaxy structure. Without such feedback, theoretical models predict galaxies would grow too large and form stars too rapidly. These bubbles, some hundreds of thousands of light years across, displace gas and drive turbulence, redistributing energy and metals. The long-term impact of these jets helps determine the temperature, pressure, and chemical composition of vast cosmic regions. In the early universe, black hole-driven winds may have played a critical role in reionization, the cosmic era when the first stars and galaxies relit the universe after the Dark Ages. By ionizing surrounding hydrogen gas, these early black holes helped shape the transparency and structure of the cosmos, contributing to the conditions necessary for light to travel freely across space. Although Einstein's theory has passed every experimental test to date, it remains incomplete. It does not incorporate quantum mechanics, nor does it explain dark energy or dark matter. Black holes, by virtue of their extreme environments, offer a natural setting to search for cracks in the theory. Any such deviation would be of enormous significance, signaling a need for a new theory of gravity. Such a theory might unify the known forces, reconcile quantum mechanics with curved space-time, or reveal hidden dimensions. Each of these ideas offers predictions that can, in principle, be tested with precise measurements of black holes and their interactions. In some quantum gravity models, this semi-reflective surface could generate delayed gravitational signals, faint repetitions of the original merger waveform. While no confirmed echoes have been detected, searches continue with increasing sensitivity. Some theories suggest that dark matter could consist of stable, massive particles that accumulate near black holes, affecting their accretion dynamics or orbital motion. Others propose the existence of dark photons or axions, hypothetical particles that could form clouds around spinning black holes and produce unique gravitational wave signatures. These particles may interact only gravitationally, making them difficult to detect in laboratories, but potentially observable through their effects on black hole behavior. Others explore the role of black holes in computational limits, how fast information can be processed, or how long it takes to scramble data. These ideas connect physics with the foundations of information theory, suggesting deep links between computation, thermodynamics, and the fabric of space-time. Though speculative, these connections reflect a growing recognition that black holes are not just objects in space. They are conceptual tools for understanding reality itself. Whether viewed as a gravitational trap, an information processor, or a bridge between worlds, the black hole stands at the heart of modern physics. And though we may never cross an event horizon ourselves, our understanding circles ever closer, drawn by curiosity, shaped by inquiry, and illuminated by light that barely escaped the edge. This interplay is nowhere more evident than in the emerging field of multi-messenger astronomy, where gravitational waves, electromagnetic radiation, and neutrinos are used in concert to study the same cosmic events from multiple angles. Black holes, especially during mergers or when they interact violently with nearby matter, can emit signals across all three channels. Detecting these events in multiple messengers not only enriches our understanding, but allows us to test the consistency of physical laws under extreme conditions. When detected together, these signals could unravel the properties of dense nuclear matter, the dynamics of relativistic jets, and the formation of heavy elements through rapid neutron capture. Though such an event has yet to be observed in all three messengers simultaneously, preparations are underway with coordinated observatories around the world. Pinpointing the source of these bursts requires precise timing and localization, which gravitational wave detectors and space-based gamma-ray telescopes are now beginning to achieve in tandem. Upcoming missions such as the Laser Interferometer Space Antenna, LISA, a joint effort by ESA and NASA, will detect gravitational waves in the millihertz range, ideal for tracking massive black hole binaries during their long in-spiral phase. Unlike ground-based detectors, which are sensitive to brief high-frequency signals, LISA will capture the slow dance of black holes over months and years, revealing not just their mergers, but their migration through galaxy mergers and cosmic structures. These backgrounds carry information about the population of black holes throughout the universe and the processes that formed them. Detecting and analyzing these subtle signals will require sophisticated data analysis techniques, but the rewards could be profound. a new map of the gravitational universe layered atop the electromagnetic one we already know. By observing high redshift quasars, faint galaxies, and the intergalactic medium, these instruments will help trace the growth of black holes in the cosmic dawn. They may also reveal the environmental conditions that nurtured or hindered their development, including the role of metal-poor gas, stellar feedback, and large-scale structure. These signals are incredibly faint and slow, requiring years of data, but their detection would open yet another observational window. By combining pulsar observations from around the globe, researchers are effectively constructing a galaxy-sized gravitational wave detector sensitive to the deep background rhythms of black hole motion. They are no longer viewed merely as endpoints, but as active participants in cosmic processes. They regulate galaxy formation, catalyze stellar death, shape dark matter halos, and encode the deepest riddles of space-time. While black holes are defined through the language of mathematics and revealed through the tools of science, their significance reaches into the realm of metaphysics and meaning. They compel us to ask not only how the universe works, but what it means for something to be knowable at all. In the equations of general relativity, this is where the model breaks down, signaling the need for a deeper theory. Yet the singularity is not a physical object in the traditional sense. It is a boundary, a limit to predictability, a horizon of understanding. We cannot observe it directly, and we cannot test its properties with known tools. It exists as a placeholder for physics yet to come. In cosmology, the Big Bang is often described as a kind of singularity, a point beyond which our models fail. In quantum mechanics, measurement outcomes are probabilistic, with information encoded in non-local entanglements. In both realms, the limits of knowledge are not just technical, but conceptual. Black holes bring these limits into sharp relief. They are the crossroads where epistemology meets ontology, where the question of what is real converges with the question of what can be known. Instead of seeking a single equation to describe the interior, we might come to understand black holes as emergent phenomena, macroscopic manifestations of deeper microphysical rules. In this framework, the event horizon is not a sharp boundary, but a statistical average over many microscopic states. The singularity is not a point, but a breakdown of coarse-grained description. Reality, in this view, is not a fixed stage, but a process of unfolding from simpler rules. Black holes, as the most entangled systems in nature, become the crucibles in which this emergent structure is forged. Every black hole contains a history, a ledger of the mass and energy that fell into it. Though the details are obscured, the influence remains. In this way, black holes preserve memory, not in the form of images or language, but in the curvature of the cosmos. Their presence is a record of what was, even if the past cannot be retrieved. They challenge our models, our instruments, our assumptions. They invite us to explore, to imagine, to reach beyond the visible and the known. They are not merely the ends of stars, but the beginnings of inquiry. They are the points at which time halts, yet they propel us forward, compelling us to ask deeper questions and seek broader perspectives. In black holes, we have found a modern incarnation of these ancient mysteries, now articulated with the tools of modern science. And each step has brought us closer to the horizon, not just of a black hole, but of our own understanding. In refusing to yield all their secrets, black holes keep us searching. They remind us that knowledge is not a destination, but a path. That mystery is not the absence of answers, but the presence of deeper questions. And that the universe in all its vastness still holds wonders we have yet to imagine. It holds within it not only mass and energy, but possibility, and in its gravity, we find a direction, a pull toward the unknown. And though we may never cross the event horizon, we continue to approach it, driven not by certainty, but by wonder. Their growth, movement, and interactions alter their environments in measurable, often dramatic ways. Yet at the hearts of merging galaxies, the supermassive black holes do not dance around each other indefinitely. Instead, they spiral inward, losing energy through dynamical friction and eventually gravitational waves until they merge into one. The final merged black hole may receive a recoil, a kick, from asymmetrical gravitational wave emission. If this kick is strong enough, the black hole may be ejected from the galactic center. In other cases, the black hole remains but ignites a new phase of activity, feeding on gas stirred by the merger and launching jets that heat the surrounding interstellar medium. By heating and expelling gas, the active black hole can suppress the birth of new stars, but it can also trigger star formation by compressing gas in certain regions. The precise balance depends on the geometry, the timing, and the conditions of the merger, a complex, sensitive interaction with long-term consequences for galactic morphology. Clusters grow by drawing in members along cosmic filaments, and black holes grow by accreting mass and merging with other black holes. This hierarchical process is the backbone of large-scale cosmological models. It suggests that the distribution of black hole masses we observe today is a cumulative product of countless prior interactions, each one sculpted by gravity and time. Using supercomputers, astrophysicists recreate the growth of dark matter halos, the inflow of gas, the ignition of star formation, and the coalescence of galaxies. These simulations, such as Illustris and Eagle, have become increasingly sophisticated, incorporating feedback from supernovae, magnetic fields, and black holes themselves. They produce virtual universes that match many observed properties of our own, including the mass function of galaxies, the clustering of matter, and the distribution of black hole masses. The answers lie not just in the amount of gas available, but in the angular momentum of infalling material, the presence of stabilizing structures like galactic bars, and the chaotic history of minor interactions. Rubin Observatory's upcoming Legacy Survey of Space and Time, LSST, aimed to catalog billions of galaxies, tracking their shapes, sizes, star formation histories, and central black hole activity over time. By comparing these massive data sets, researchers hope to tease out the patterns that link black holes to their hosts and to understand the full range of evolutionary paths galaxies may take. Traditionally, astronomers have relied on standard candles, objects like type Ia supernovae, whose intrinsic brightness is well known, to determine cosmic distances. But recent work suggests that black hole mergers could serve as standard sirens. When two black holes collide, the amplitude and frequency of the resulting gravitational waves encode their distance. If the host galaxy of the merger can also be identified through electromagnetic signals, then the redshift can be measured and a direct relationship between distance and redshift established. Standard sirens could help resolve this tension, providing a new pillar for the cosmic distance ladder that is rooted in entirely different physics. In particular, the tight correlation between black hole mass and stellar velocity dispersion, the m-sigma relation, offers a window into the co-evolution of galaxies and their central engines. These deviations could be detected through precise timing of pulsars orbiting near black holes, or through the shape and brightness of the photon ring around the event horizon. Even tiny deviations from expected patterns could hint at new forces, extra dimensions, or quantum corrections. Just as atoms emit light at characteristic frequencies, when electrons change energy levels, black holes emit gravitational waves at specific frequencies during ringdown. These frequencies depend only on the black hole's mass and spin, making them ideal for testing the no-hair theorem. If discrepancies are found, if the observed frequencies cannot be explained by general relativity alone, it could signal new physics at work. Black holes, once thought to be featureless voids, are turning out to be among the most informative objects in the universe. By comparing these simulations to real data, scientists refine their models and build an ever more accurate picture of how gravity behaves in its most extreme form. Some theorists have drawn parallels between the way black holes mix information and the way quantum circuits process it, suggesting deep connections between gravity and computation. The holographic principle, once a radical idea in string theory, now finds application in understanding superconductivity, fluid dynamics, and quantum critical systems. Their mathematical elegance, physical extremity, and philosophical depth make them ideal laboratories not only for nature, but for thought. They speak to human curiosity and our desire to understand what lies beyond. They are, in a real sense, the memory of the universe, preserving the imprint of what has passed, even as they reshape what is to come. They reward persistence and they punish assumptions. As cosmic time stretches forward, the processes that drive the evolution of galaxies and stars will gradually slow. Stars will exhaust their nuclear fuel and die. Star formation will dwindle as available gas is used up or dispersed. The universe will grow colder and darker, entering what is sometimes called the degenerate era, a time dominated by long-lived remnants like white dwarfs, neutron stars, and black holes. While white dwarfs may eventually cool into invisible black dwarfs and neutron stars may decay via hypothetical proton decay over unimaginable timescales, black holes persist as gravitational wells in space-time, unchanged unless they merge or slowly evaporate through Hawking radiation. This slow leakage of mass energy is almost imperceptible now, but across timescales of 10 to 100 years and more, it becomes the dominant process shaping the thermodynamic landscape of the universe. Over time, even the most massive black holes are expected to lose mass, shrinking gradually until they release their final burst of radiation. This decay may be complete, or it may leave behind a stable remnant. We do not yet know. Their evaporation represents the last chapter of energetic transformation in the cosmos. The radiation they emit is low energy and sparse, but it carries entropy and information, maintaining the thermodynamic arrow of time as the universe marches toward equilibrium. This final state, sometimes called the heat death of the universe, marks the maximum entropy configuration, a state of uniformity with no free energy left to do work. But even this seemingly empty future is shaped by the legacy of black holes. They are the last sculptors of energy, the last emitters of structured radiation, the final echoes of gravitational memory. It reveals how these compact objects, formed from collapse and destruction, become the guardians of the future. They do not merely consume, they process, store, and eventually return energy to the cosmos in the most patient manner imaginable. If black holes can preserve information through Hawking radiation or through some deeper, non-local quantum mechanism, then the ultimate fate of the universe may not be pure erasure. Instead, it may be dispersal, a gradual unspooling of complexity back into the vacuum, encoded in faint correlations between distant particles, faint whispers of what once was. It expands, cools, and dies, but is then reborn in a new Big Bang, seeded perhaps by a bounce or a transition in a higher dimensional space. In such scenarios, black holes may play a pivotal role, not only as endpoints but as agents of renewal. They may collapse not into singularities, but into bridges. They may, through unknown quantum gravitational effects, initiate the next phase of creation. They mark the outer edge of our current theories, and they beckon us toward what comes next. They are the junction points where the laws of physics converge, and where they also fray. Each new discovery, each signal, each image, each formula adds tension to that web, refining its structure, making it stronger, and revealing its hidden harmonies. We have modeled their behavior on supercomputers, recreated their properties in laboratories, and woven them into the deepest narratives of theoretical physics. Every answer yields more questions. In its silence, a question. In its gravity, a call. They are not the end of the story, but its unfolding. Black holes are not simply the end points of matter, but laboratories where the rules are rewritten in ways both precise and perplexing. In this view, known as emergent space-time, gravity is not a force in the traditional sense, but a manifestation of statistical behavior among microscopic degrees of freedom. This idea aligns with black hole thermodynamics, which already suggests that entropy, surface area, and information are tightly bound together in ways that classical geometry cannot fully explain. Some models even suggest that the wormhole-like geometry predicted by Einstein-Rosen bridges could be understood as a geometric representation of quantum entanglement, a literal link formed by shared information. It proposes that Einstein-Rosen bridges, ER, and Einstein-Podolsky-Rosen, EPR, entangled particle pairs are two sides of the same coin, that the fabric of space-time is stitched together by the same phenomena that connect quantum particles across distance. If true, then the geometry of black holes, those deep warps and folds of space-time, is not merely a backdrop for physics, but the very expression of quantum correlations. In such a universe, locality becomes approximate, not absolute. Information need not be confined to a single trajectory through space-time, but can be encoded non-locally through the structure of the entangled state. A black hole's interior, which we cannot access directly, might still be inferable through its entangled radiation, a sort of quantum holography that preserves wholeness even when access is restricted. Reconciling it has required rethinking everything from entropy to geometry, from the meaning of a particle to the nature of time itself. The breakdown of temporal intuition near the event horizon is not just a mathematical curiosity, it is a signpost pointing to the limits of classical thinking. In this view, matter does not fall into a point of infinite density, but is transformed through a phase transition, its quantum state reorganized in a way that preserves unitarity, even if we cannot yet describe it fully. Gravitational wave echoes, quantum correlations in Hawking radiation, the structure of photon rings, and the behavior of matter near the innermost stable orbits, all these offer potential clues. Each observation is a data point in a broader puzzle, a fragment of a picture still being assembled. They challenge what we believe about causality, about locality, about continuity. They remind us that even the most solid foundations of science are subject to refinement, and that the universe is always more surprising than we imagine. From the earliest moments of the universe, fractions of a second after the Big Bang, conditions may have existed that permitted the formation of black holes not through stellar collapse, but from density fluctuations in the primordial plasma. These so-called primordial black holes are unlike any we have observed from dead stars. They could range in size from microscopic to massive, and may have formed directly from the collapse of overdense regions in the expanding early universe. Some may have evaporated through Hawking radiation by now, while others, depending on their initial mass, could still persist. lurking in galactic halos, passing quietly between stars, or even at the centers of dwarf galaxies. Decades of searches for dark matter particles have yet to yield direct evidence. In this context, primordial black holes have been proposed as a compelling alternative or partial contributor to the dark matter budget. If they exist in sufficient numbers and within a specific mass range, they could account for the gravitational effects attributed to dark matter. Some of these may point toward a non-stellar origin, though the evidence remains inconclusive. If future data reveals a population of black holes that do not fit neatly into models of stellar evolution, the case for primordial black holes could grow stronger. More than just curiosities, these black holes could serve as fossil records, dense, ancient artifacts from the universe's first heartbeat. This flips the usual narrative, where galaxies form first and black holes grow within them. Here, the black holes come first, acting as gravitational scaffolding for a cosmic structure. Instruments like LISA and the JWST are expected to provide critical data in the coming decades. Black holes can spin up or down as they accrete matter, grow through mergers, and even recoil when gravitational waves are emitted asymmetrically. Their evolution is active, their history encoded in their spin, mass, and motion. Quasars, blazars, and X-ray binaries all owe their brightness to the efficiency with which black holes convert gravitational energy into radiation. In these systems, matter in the accretion disk is heated to millions of degrees, emitting copious X-rays and gamma rays before falling in. Magnetic fields in the inner disk can twist and reconnect, launching jets of plasma along the rotation axis at near-light speeds. As they pierce through interstellar and intergalactic media, they inflate cavities, trigger shock waves, and inject magnetic fields. They help regulate star formation, transport energy across vast distances, and establish long-range coherence in otherwise chaotic systems. Models such as the Blandford-Znajek process describe how energy can be extracted from a spinning black hole's ergosphere via magnetic fields, while other models focus on the role of magnetized accretion flows. Simulations of magnetically arrested disks, where infalling matter builds up strong magnetic pressure near the horizon, have shown jet-like structures emerging naturally from the interaction of gravity and plasma physics. Observations of quasars and X-ray binaries show that these systems flicker and flare in complex patterns, suggesting that the dynamics near the event horizon are rich and multi-layered. Time-domain astronomy, the study of how cosmic objects change over time, is now a central part of black hole science. By measuring the Doppler shifts and relativistic broadening of emission lines, astronomers can map the motion of gas just outside the event horizon. These observations allow tests of general relativity and help constrain the geometry and spin of black holes in diverse environments. The Fermi bubbles, giant gamma-ray structures extending above and below the Milky Way's core, are thought to be relics of a previous outburst from Sagittarius A, our central black hole. Though it is now quiescent, archival X-ray studies suggest it was more active a few million years ago, possibly due to a nearby gas cloud or star being disrupted. They are in constant conversation with their surroundings through radiation, jets, winds, and gravity. Their influence extends far beyond their event horizons, shaping environments on scales from subatomic to intergalactic. They are participants in galactic evolution, regulators of star formation, engines of feedback, and timekeepers of cosmic history. And in every role, they blur the boundary between what we can observe and what we must infer. These zones are where general relativity's predictions are pushed to their limits. gas orbits at relativistic speeds. Light is bent into tight loops. Time dilates so severely that the rest of the universe seems to accelerate from the perspective of an infalling observer. The Event Horizon Telescope, EHT, has already resolved the shadow of M87 Thales, and images of Sagittarius A sign have followed. But new upgrades, including increased baseline coverage, more sensitive detectors, and advanced calibration techniques, promise even more detailed reconstructions. With these tools, scientists aim to resolve time-dependent features in the inner accretion flow, such as hotspots, flares, and orbiting plasma clumps. Any measurable deviation from these predictions could signal new physics, modifications to gravity, evidence of quantum structure near the horizon, or unexpected matter interactions. In Sagittarius A, where the timescales are shorter and the dynamics more turbulent, polarization variability may soon uncover new details about disk evolution and the role of magnetic pressure. While general relativity defines a black hole as a region bounded by an event horizon, quantum theories suggest alternative possibilities: fuzzballs in string theory, gravastars, black stars, or firewalls. Each of these models aims to resolve paradoxes like information loss, or to describe the microstructure of space-time. None have been confirmed, but all remain active areas of study. If firewalls exist, they would represent a breakdown of the equivalence principle, a cornerstone of general relativity. And it serves as a reminder that black holes are not only astrophysical objects, they are crucibles where the deepest laws of nature intersect. These ideas, though speculative, are grounded in the belief that singularities are signs not of physical reality, but of the breakdown of classical description. Within this granular structure, extreme densities and curvatures may be regulated by quantum repulsion, much as electron degeneracy pressure stabilizes white dwarfs, or neutron pressure halts further collapse in neutron stars. In this picture, black holes and white holes could be two sides of the same coin, connected through a quantum transition that occurs inside the horizon, but invisible to external observers. Over vast timescales, as a black hole evaporates, it might transform into a white hole, releasing its stored information in a final burst. For example, the final stage of black hole evaporation might produce a distinctive radiation signature. If detected, such a signal could reveal details about the structure of spacetime at the smallest scales and confirm the presence of quantum gravitational effects. This idea, central to the ad estem CFT correspondence, has gained traction as a framework for describing black hole entropy and interior structure. It suggests that what we perceive as a volume of space may actually be encoded on a boundary, and that the connectivity of space is defined by information rather than position. Their event horizons are not barriers to understanding, but membranes through which information flows in subtly encoded ways. If we can decipher that encoding, we may one day reconstruct not just the mass and spin of a black hole, but the history of everything that has fallen into it. If the universe itself is holographic, if its geometry arises from entanglement, then black holes are not exceptions, but exemplars. They are places where the underlying structure is exposed, magnified, and compressed. They are natural laboratories for the emergence of space, time, and causality from a deeper, more abstract substrate. But they point in a common direction, toward a vision of the universe in which black holes are not the ends of things but portals. Not places of death, but of transformation. Not blind spots, but windows into the next chapter of physics. They embody the paradoxes at the heart of modern physics, the deterministic flow of space-time, described by general relativity versus the probabilistic, information-preserving nature of quantum mechanics. Resolving these contradictions is not simply about understanding black holes, it's about completing the story of the universe itself. One of the most active areas of theoretical physics centers on quantum error correction, a branch of quantum information theory originally developed for building robust quantum computers, but now recognized as deeply linked to the fabric of space-time. This aligns with the holographic principle, where all the information in a volume is stored on its boundary. Black holes, then, are the most efficient scramblers of information in the universe, reducing complex, ordered states into highly entropic surface encodings, but never truly destroying the data. In this way, the event horizon is not a one-way veil, but a transitory stage in a quantum communication process that may be reversible in principle, if not in practice. But the central theme is elegant. The structure of space and time may be a code, a highly redundant, fault-tolerant, self-correcting quantum code that naturally protects and distributes information. This offers not just a way to preserve information, but a vision of space-time as a computational process. It is no longer just a gravitational sink, it is an information processor, a thermodynamic object, a quantum system in dialogue with the universe. Its entropy, proportional to the surface area of its horizon, reflects not the disorder within a volume, but the number of distinguishable quantum states that can reside on its boundary. In a scenario where information is preserved, the entropy of radiation rises at first but then falls as the black hole loses mass, resulting in a curve that resembles an arch. This was once thought incompatible with semi-classical models of Hawking radiation, but newer quantum gravity models, including those using island prescriptions and gravitational path integrals, have successfully reproduced the Page curve. These results strongly suggest that unitarity, the cornerstone of quantum mechanics, remains intact even in the presence of black holes. The Next Generation Event Horizon Telescope, NGEHDC, will dramatically increase the number of telescopes in the global array, enhancing sensitivity and imaging capability. It aims to capture real-time dynamics, changes in brightness, polarization, and structure in the innermost regions around black holes. Facilities like the Einstein Telescope and the Cosmic Explorer will push the limits of sensitivity, allowing black hole mergers to be detected at redshifts of 10 and beyond. This means observing black holes as they existed in the first few 100 million years after the Big Bang, when the universe was still assembling its earliest structure. Such detections will help determine whether black holes formed from stars, gas cloud collapse, or more exotic mechanisms in the primordial soup. It will detect mergers with tens of thousands or millions of solar masses, objects that are otherwise invisible to current instruments. These detections will help complete the picture of black hole growth, mapping out the pathways through which galaxies and their central engines evolve together. In combination, these facilities will produce a multi-messenger view of black holes, connecting gravitational waves, electromagnetic radiation, and potentially neutrinos into a coherent picture. Already, neural networks are being trained to classify merger events, reconstruct source parameters, and predict black hole properties from indirect data. The goal is not only to detect and describe black holes, but to interpret them, to embed them within a narrative of cosmic evolution that unifies observation and theory. Not of loss, but of transformation. They exist across a spectrum of masses, environments, and behaviors. At one end are stellar mass black holes formed from the collapse of massive stars. These are scattered throughout the Milky Way and other galaxies, often detectable only when paired with a companion star or when their gravity briefly lenses background starlight. Their mass distribution, typically ranging from a few to tens of solar masses, reflects the life cycles of the stars that birthed them. Their presence in almost every massive galaxy implies a universal process of coevolution, though their origin remains a subject of debate. Did they grow slowly from stellar remnants, or did they form early from the direct collapse of primordial gas clouds? With masses between 100 and 100,000 solar masses, these black holes are thought to reside in globular clusters, dwarf galaxies, or perhaps the centers of ancient, now merged star systems. Until recently, they remained theoretical, with few clear detections. But gravitational wave observatories have begun to uncover candidates in this mass range, suggesting that IMBHs may be more common than once thought. They may form through repeated mergers of stellar mass black holes in dense stellar environments, or through the collapse of massive, low metallicity stars in the early universe. Their existence could help explain the rapid emergence of supermassive black holes in the young cosmos, serving as early seeds that grew over time through accretion and hierarchical merging. The spin of a black hole affects the shape of the event horizon, the efficiency of accretion, and the structure of the surrounding space-time. Rapidly spinning black holes can release more energy from infalling matter, power stronger jets, and influence the evolution of their host environments. By analyzing X-ray spectra of accretion disks, the reflection of light from the inner regions near the event horizon, and gravitational waveforms from mergers, astronomers can infer spin parameters with increasing precision. Patterns in spin distribution may reveal clues about formation channels. For example, aligned spins in binary black holes might indicate a common origin in a stellar system, while misaligned spins may suggest dynamical capture in dense clusters. Still others may undergo episodic outbursts, switching between active and dormant phases depending on the availability of gas. This variability is seen in both X-ray binaries and active galactic nuclei, and tracking it over time helps map the life cycles of these complex systems. While we often think of them as stationary objects, black holes can move, kicked by gravitational recoil, accelerated by galaxy mergers, or even wandering freely in the halos of galaxies. These rogue black holes, untethered to any visible structure, may outnumber their more luminous counterparts. Detecting them requires ingenuity, gravitational lensing, perturbations in stellar motions, or subtle distortions in background light. Though still in the realm of speculative physics, proposals for using black holes as energy sources, gravitational laboratories, or even computational devices are gaining theoretical rigor. If a particle splits near the ergosphere, one fragment may fall into the black hole with negative energy from the perspective of infinity, while the other escapes with more energy than the original particle possessed. Though currently impractical, the principle illustrates how black holes might be used as ultra-efficient power plants. A civilization capable of creating or capturing a black hole of specific size could, in theory, harness its output for computation, propulsion, or life support over trillions of years. The Bekenstein bound, which relates entropy to information, implies that black holes are the most efficient storage devices in the universe. If their dynamics could be controlled, black holes might be used to perform computations beyond the reach of ordinary matter-based systems. Hawking radiation from the black hole is directed via mirrors to generate thrust. Such a ship, while extraordinarily challenging to construct, could theoretically accelerate to near light speed and sustain life aboard indefinitely, powered by the decay of its own onboard singularity. They speak not only to what black holes are, but to what they could be, if harnessed, if controlled, if understood fully. What role might black holes play in a long-lived cosmic society? whether as energy sources, knowledge vaults, or memory banks. It challenges us to think in terms of cosmic engineering, where the tools are space-time itself and the constraints are nothing less than the laws of physics. They are illuminating, showing us what is possible, what is thinkable, and what is yet to be known. Their existence compels a merger of disciplines that have historically stood apart: general relativity and quantum mechanics, thermodynamics and information theory, astrophysics, and quantum field theory. Black holes are the testing ground for this new physics, the crucibles where the known laws are pushed to their breaking point. Whether in the form of string theory, loop quantum gravity, causal set theory, or other approaches, every candidate theory must confront the challenge posed by black holes and reconcile their entropy, their information content, and their ultimate fate. The idea that space-time might not be fundamental, but rather a large-scale pattern emerging from microscopic entanglement, transforms the way we interpret gravity. It suggests that gravity is not a force, but a consequence, a thermodynamic response of a deeper quantum system. In this paradigm, black holes become not just objects, but phases of quantum matter, states that exhibit extreme entropy, symmetry breaking, and collective behavior. In this view, black holes serve as condensation points of relational information, a kind of cosmic knot, where the threads of the quantum universe are pulled into the tightest possible weave. The Bekenstein-Hawking formula, which equates a black hole's entropy to the area of its horizon divided by Planck length squared, remains one of the most profound results in theoretical physics. It bridges geometry and thermodynamics, area and information, surface and volume. And it hints that all of space-time might be governed by similar principles, that the horizon of a black hole is not unique in carrying entropy, but rather an example of a general rule. The de Sitter horizon of our accelerating universe, the Rindler horizon of a constantly accelerating observer, even the apparent horizons in certain fluid analogs, each may encode information in ways that mirror black holes. This generalization suggests a deep unity between gravity, acceleration, and thermodynamics. While still speculative, some theorists have begun to ask whether the flow of information through horizons, whether black hole horizons or cognitive ones, may be subject to similar principles. Could the limits of perception, the boundary between known and unknown, mirror the event horizon's role in the physical universe? They point to a growing awareness that the study of black holes is also the study of boundaries between the known and the unknowable, the observer and the observed, the interior and the exterior. In grappling with the physics of black holes, we are not merely chasing answers, we are refining the questions themselves. Not silence, but the encoded hum of information waiting to be deciphered. They are the repositories of time, the keepers of entropy, and the gates through which theory must pass to glimpse the next frontier. They demand intellectual humility, yet reward us with astonishing coherence when approached on their terms. Not to close the book, but to write the next chapter. They are pauses, gateways, transformations. As the theoretical lens continues to sharpen, we find that black holes not only thread together disciplines within physics, but increasingly offer insights that echo into areas we might not have expected, from computational theory to cosmogenesis, from biological analogy to philosophical inquiry. While no reputable theory claims that black holes possess or transmit consciousness, some frameworks inspired by black hole physics have analogized the human brain as an entropic processor, a structure that, like a black hole's event horizon, encodes and transforms information on a boundary surface. Though speculative and metaphorical, These analogies serve to remind us how deeply black holes have entered our conceptual vocabulary, not only as physical entities, but as models for processing, boundary, and transformation. Seth Lloyd, a quantum information theorist, once proposed that the ultimate computer, the most powerful computational device that could physically exist, might be a black hole. According to the Bekenstein bound, the maximum amount of information that can be stored within a finite region of space, with a finite amount of energy, is proportional to the area of the boundary surface, not the volume. In this sense, black holes are the most efficient memory storage units possible under known physical laws. But if Hawking radiation eventually reveals information in a scrambled format, as some models now suggest, then that compression may still be invertible in principle, albeit unimaginably complex. If Hawking radiation is entangled with both earlier radiation and with the interior of the black hole, a contradiction appears. Some resolutions propose that the interior is destroyed, replaced by a firewall of high-energy particles that breaks the equivalence principle. Instead, newer frameworks, including entanglement wedge reconstruction in SCFT, suggest that information about the black hole's interior is encoded non-locally in the radiation without requiring any physical drama at the horizon itself. In these models, space-time geometry arises from entanglement patterns, and bulk observables, what's inside the black hole, can, under the right circumstances, be reconstructed from boundary data. In this view, an event horizon does not block access in an absolute sense. It sets the conditions under which reconstruction is possible. Time, too, may be a consequence of entanglement's directionality, the arrow of time emerging from the growth of entanglement entropy in subsystems. Their evaporation via Hawking radiation, if unitarity holds, preserves global information while reshuffling its local form. But in an emergent space-time framework, the merger represents not just a geometric process, but a restructuring of quantum information networks. The final black hole is a new quantum state, defined not only by mass and spin, but by its entanglement structure with the rest of the universe. This principle posits that different observers may describe the same black hole using different but consistent accounts. For an outside observer, infalling matter appears frozen at the horizon, its information encoded in the stretched surface. For the infalling observer, the journey proceeds smoothly through the horizon toward the singularity, or whatever replaces it in quantum gravity. These views cannot be combined into a single global picture, but they are not in conflict because no observer can experience both. What exists and what is accessible depends not only on location, but on causal history and observational constraints. And if so, what is encoded on that cosmic screen? This expansion resembles, in its causal structure, a kind of cosmological horizon, not unlike a black hole's event horizon in reverse. The observer inside can see only a limited patch of space, and the rest lies forever beyond communication. Does the cosmic horizon carry entropy? Is information encoded there? Do holographic limits apply at cosmological scales? In such a framework, everything we observe would be a projection from this boundary theory. Their horizons are echoes of the limits of observation that define our place in the cosmos. Why is the value so small, yet non-zero? Could it be related to the entanglement entropy of the cosmic horizon? Could it signal a deeper holographic principle at work? As prototypes for the deep structure of reality. This idea, known broadly as cosmological natural selection or fecund universes, proposes that each black hole might not simply mark an end, but a beginning. According to this hypothesis, a black hole's singularity may serve as the initial state for a new expanding universe, one that buds off from our own, as if through a cosmological branching. Thus, just as biological evolution favors traits that maximize reproductive success, cosmological evolution would favor the emergence of universe structures and physical constants that encourage black hole formation. It invites us to consider whether the conditions in our own universe, such as the masses of elementary particles, the strengths of fundamental forces, or the behavior of gravity, might have been shaped by a kind of selection pressure that rewards black hole fertility. The idea is bold, certainly speculative, and difficult to test, but it offers a framework for explaining why the universe seems so finely tuned for the existence of stars, galaxies, and complex structure. Our own Big Bang might have originated in such a seed, born not from nothing, but from the core of a black hole in some larger, unknowable parent cosmos. Instead of a true point of infinite density, the collapsing core of a black hole reaches a minimal volume, then rebounds into expansion. This bounce may be instantaneous from an interior point of view, but appear frozen in time to an external observer. In this framework, discrete units of volume and area replace the smooth continuum of classical geometry, and the singularity is avoided through quantum corrections. While these models remain under active development, they offer a tantalizing possibility that black holes are bridges, not endpoints. They are solutions permitted by general relativity, though they require highly specific and likely unphysical conditions to remain stable. Whether these effects could scale up to macroscopic wormholes remains speculative. In this model, entangled particles are not merely linked statistically but geometrically through a tiny Planck-scale thread of space-time. These scenarios exploit the mathematical similarity between teleportation protocols in quantum information theory and the equations governing traversable wormholes in anti-de Sitter space. Though still deeply hypothetical, these models suggest that information may traverse space-time in ways far more subtle than simple particle motion. These concepts occupy the outer edges of the Kardashev scale, a framework for categorizing civilizations by their energy use. A Type II civilization capable of harnessing the full power of a star might build a black hole Dyson sphere or direct Hawking radiation for power. A Type III civilization managing galactic energies might deploy wormholes as instantaneous information pathways or as escape routes from cosmic disaster. But their feasibility in terms of physical law is often bounded not by outright impossibility, but by engineering capacity, energy scale, and stability. The physics of black holes suggests that space, time, and energy may be manipulated in principle, even if not yet in practice. In the far reaches of cosmological time, long after the last stars have burned out and galaxies have dispersed, black holes will continue to exist, slowly radiating their mass away through Hawking radiation. Eventually, these remnants will dwindle, their mass transformed into radiation that diffuses across an ever-darkening cosmos. And in their death throes, they may seed the birth of something else, a new inflation, a rebirth of space-time, or an informational signature that loops the universe into a cycle. They mark both origin and end, boundary and bridge. Each merger, each accretion disk, each flicker of high-energy radiation is a sentence in a book whose language we are only beginning to decipher. These laboratory systems mimic aspects of general relativity by creating environments where phenomena like event horizons or Hawking-like radiation can be studied in controlled settings. Though not black holes in the astrophysical sense, these simulated analogs involving fluids, Bose-Einstein condensates, and optical waveguides allow physicists to probe the foundational principles of horizon thermodynamics. Stephen Hawking himself proposed that such a system could emit analogs of Hawking radiation, demonstrating the universality of the phenomenon across different physical substrates. These experiments do not replicate the intense gravitational fields of true black holes, but they test whether horizons alone, regardless of their origin, suffice to produce radiation-like behavior. That the event horizon, as a geometric limit, induces universal responses in the vacuum, even when no real singularity is present, points toward a thermodynamic essence that transcends specific space-time geometries. They are becoming interdisciplinary gateways, linking fields once thought unrelated and encouraging a new mode of scientific synthesis where ideas migrate across domains to uncover universal principles. Whether through emergent geometry, holographic dualities, or laboratory analogs, black holes are teaching us that laws may arise from structure, that gravity may be a consequence, and that the universe is governed not only by particles and fields, but by information, correlation, and horizon. As matter collapses toward a singularity, the density and energy levels exceed those of any known state. It is here, at these extremes, that unknown particles and forces may briefly emerge before being hidden forever behind the veil of the horizon. If miniature black holes can form, either in high-energy collisions or in the early universe, then their decay products might betray the presence of supersymmetry, extra dimensions, or other exotic phenomena. The Large Hadron Collider, despite its current energy limitations, has inspired searches for such fleeting micro-black holes, though none have yet been observed. Deviations from general relativity's predictions, such as altered waveform tails, irregular ring-down patterns, or anomalous recoil velocities, could signal modifications to gravity itself, or hint at hidden structure inside the merging bodies. Though data so far aligns well with Einstein's theory, future detections at greater sensitivity may yet uncover subtle anomalies. If nature permits interactions in these regions, it might allow particles to be accelerated to transplanckian energies, perhaps triggering rare events that could illuminate otherwise unreachable laws. They are the crucibles where classical and quantum, thermodynamic and geometric, global and local meet. But each one we explore, each observation we make, each equation we test, leads us closer to what the fabric of the universe truly is, not as we imagine it, but as it must be. From the stellar remnants collapsed under their own weight, to the cosmic engines shaping galaxies, to the theoretical constructs bridging quantum and gravitational realms, black holes encompass every scale and every boundary. They challenge what we know about time, space, and entropy, and whisper that those may not be fundamental concepts after all. We have imagined them as laboratories, computers, gateways, and mirrors of the cosmos itself. And in doing so, they invite wonder. They are the structure behind structure, the entropy behind energy, the mystery behind motion. This proposal is not limited to black holes. In certain quantum gravity models, including string theory and ADS-CFT correspondence, the holographic principle is extended to the entire universe. It suggests that the three-dimensional world we perceive could emerge from encoded information on a two-dimensional boundary. If so, then the laws of gravity and space as we understand them are not fundamental but emergent, a shadow of deeper principles operating from the boundary inward. Within this framework, the black hole becomes more than a cosmic curiosity. It becomes a proof of concept, a window into the machinery of existence itself, a laboratory not just for extremes of mass and temperature, but for the very structure of information and its entanglement with geometry. This reframing leads naturally into ideas where space-time is not a backdrop, but a product. That distance and curvature are not intrinsic, but derivative. That the deep stitching of entangled quantum fields gives rise to the illusion of continuity, location, and gravity. The black hole, by compressing this entanglement to its extreme, reveals the hidden code beneath, but not all theories envision black holes as endpoints or objects of containment. Some suggest that they are in fact misinterpretations, that what we see as a black hole may not contain a singularity at all. Perhaps the matter that collapses does not vanish but transforms, arrested at a phase boundary that mimics a horizon. In these models, often called gravastars or fuzzballs, the collapse stabilizes in exotic forms, dense, hot, horizon-like, but not hiding a singularity. Such alternatives are proposed in part to resolve the paradoxes that standard black hole models create, including the firewall problem, which challenges the idea that observers can cross the event horizon unscathed. If the event horizon is instead a kind of phase transition, the nature of infalling matter and the fate of observers could be very different from what general relativity alone suggests. Another direction of speculation is time itself, its nature and direction, and how black holes may influence or invert it. In classical relativity, time slows near massive bodies. Near a black hole, this effect becomes extreme. From the outside, infalling objects appear to freeze at the edge of the horizon, never quite falling in. But from their own perspective, they fall through infinite time. This contradiction is not a flaw, but a feature of relativity, a glimpse into how time is not universal but local, and how the structure of space-time bends not only motion but chronology. In speculative cosmologies, some have proposed that black holes could be time machines, not in the science fiction sense of deliberate transport, but in the sense that their geometry permits loops of causality. These closed time-like curves appear in certain solutions to Einstein's equations, particularly in the presence of rotation or negative energy densities. Though unstable in most models, they raise foundational questions about whether time has a fixed arrow or, if under the right conditions, it might bend back on itself. Yet the more immediate question is whether black holes themselves persist across time, or if they dissolve into something stranger. One idea, emerging from quantum gravity, is that black holes do not evaporate into nothingness, but leave behind relics, stable, compact objects that store the final bits of information that would otherwise be lost. These Planck-scale relics would be undetectable by present instruments, but could in theory account for the mysterious dark matter that fills the universe. Dark matter itself is another arena of speculation. Some theorists have proposed that dark matter may consist, at least in part, of primordial black holes, ancient relics formed in the early universe before stars and galaxies. Unlike black holes born from collapsed stars, these objects would have arisen from density fluctuations in the hot, early cosmos. If they exist in sufficient numbers and masses, they could contribute significantly to the unseen mass we detect through gravitational effects. Searches for such objects continue using microlensing surveys and gravitational wave observations, but so far, no conclusive evidence has emerged. Still, the idea remains alive, another intersection between black holes and the unknown structure of the cosmos. From another speculative angle, some physicists have asked, what if black holes themselves are alive, not biologically, but as self-organizing information structures? If we view the universe as an evolving system of computation, then a black hole may represent a kind of ultimate processor, a place where data is compressed, transformed, and eventually emitted in altered form. This aligns with recent trends in physics that see information not just as a tool for understanding systems, but as a fundamental element of reality. In this view, the cosmos is not a machine, but a computation, a continually running algorithm that generates structure, entropy, and experience. Black holes, then, are not anomalies, but core components of this logic. Still deeper is the question of consciousness and observation. Some have speculated, cautiously and without mainstream endorsement, that the event horizon of a black hole may represent a boundary of perception as much as of space. That what lies beyond it is not merely unknowable in practice, but undefined in principle, a domain outside causal influence, outside narrative, perhaps even outside ontology as we know it. If that is so, then black holes are more than physical phenomena. They are limits to light, to information, to prediction, to meaning. They are the edges of maps, not just of space, but of epistemology. And yet, for all their obscurity, they speak. In radio waves, in gravitational echoes, in jets of matter flung at near-light speeds. They are not silent, but selective. They whisper only what their horizons allow. What we can hear is not their truth, but their trace. In this way, black holes are like history, not a record of what is, but of what can still be known. Throughout the history of scientific speculation, there has been a persistent thread connecting cosmic phenomena to the idea of extraterrestrial intelligence. Among the most intriguing of these conjectures is the possibility that black holes, those silent anchors of space-time, may not only be natural features of the cosmos, but could, under some interpretations, serve as technological artifacts, communication hubs, or even habitats engineered or utilized by advanced alien civilizations. This idea, while speculative, emerges naturally from the same logic that underpins the Kardashev scale, which measures the technological advancement of civilizations by the energy they can control. A Type 1 civilization harnesses planetary energy, a Type 2 controls the energy of a star, a Type 3 civilization could manipulate the energy output of entire galaxies. Within that framework, black holes are the ultimate power sources, gravitational engines, time dilators, entropy sinks, and potential data processors beyond any known efficiency. A rotating black hole, in particular, contains within it what is known as an ergosphere, a region just outside the event horizon where space-time is dragged along with the spin of the black hole. The Penrose process theorizes that it is possible to extract energy from this region by carefully entering it and splitting an object in two, with one part falling into the black hole and the other escaping with more energy than the original. For a civilization capable of operating at such scales, this would be a natural mechanism for power generation. This gives rise to the so-called black hole starships hypothesis, the idea that an advanced civilization might use small, artificial black holes as propulsion systems. A micro black hole could emit Hawking radiation, and if stabilized at a particular mass, it might serve as a virtually inexhaustible directed energy source. Theoretical physicist Lewis Crane and others have proposed that such constructs might be used not only for interstellar travel but also for computational purposes, acting as logic gates in ultra-dense computing environments. But perhaps the most radical notion is the use of black holes as communication devices. In classical physics, nothing can escape from a black hole once past the event horizon. But in quantum theories, particularly in those that deal with the information paradox, information may not be lost, but encoded in subtle fluctuations of Hawking radiation or in the shape of the event horizon itself. A civilization sufficiently advanced in quantum engineering could, in theory, modulate the outgoing radiation of a black hole to transmit signals. To less developed observers, these signals might appear as anomalous, flickering and high-energy emissions, indistinguishable from natural processes unless decoded with extraordinary precision. Alternatively, gravitational waves, the ripples in space-time produced by massive accelerations such as black hole mergers, could serve as interstellar beacons. Unlike electromagnetic signals, gravitational waves pass through all matter, cannot be blocked or absorbed, and are detectable across vast cosmic distances. A civilization using controlled black hole interactions, such as the merger of micro-black holes, might produce distinct, timed gravitational wave signatures. To us, these would appear as rare cosmic events. To them, they might be intentional broadcasts across epochs and voids. Another angle considers that black holes could serve as cosmic libraries, storage devices, where information is encoded in the configuration of matter thrown into their grasp. If the holographic principle holds, and all information is retained on the event horizon, then a highly advanced intelligence might develop techniques to read, write, and interpret this surface structure. What we see as entropy increase might to them be a form of writing, a way to encode memories, histories, or signals not in language, but in the topology of space-time. Still more speculative is the idea that black holes could be entry points into higher dimensional space, what some call hyperspace, or the bulk. In string theory and brain world scenarios, our universe may be a three-dimensional surface within a higher dimensional space. A sufficiently powerful intelligence might exploit the geometry of rotating or charged black holes, especially those with ring singularities like Kerr black holes, to navigate between branes, moving across layers of reality as easily as we cross a street. To an outside observer, such behavior might look like the sudden disappearance of energy or mass from our observable universe, or inexplicable patterns in the rotation rates or accretion profiles of certain black holes. Anomalies in X-ray emissions or relativistic jets could, in this lens, be signatures of interference, not natural quirks, but the indirect shadow of engineering at a cosmic scale. It is important to emphasize there is no direct evidence that black holes are being used by intelligent life. All observations to date are consistent with natural gravitational collapse and known physics. But in the realm of the unknown, particularly where black holes and alien intelligence intersect, the line between speculation and possibility is not always sharp. Our own limitations of perception, scale, and time bias us toward seeing black holes as ends, destructive endpoints of matter and time. But for a civilization millions or billions of years more advanced, they might be viewed not as tombs, but as tools, gateways, or even homes. If consciousness is possible in radically different substrates, as some post-biological evolution theories suggest, then perhaps the distinction between the living and the gravitational may blur. A network of orbiting constructs, using the gravitational well of a black hole to bend light, store heat, and harvest data, could host minds that think in time frames we cannot fathom, perhaps contemplating not decades or centuries, but the thermal death of the universe itself. And if such civilizations exist, their silence may not be due to disinterest, or distance, or extinction. It may be that they have withdrawn, not into space, but into the folds of gravity, where time runs slower and thought runs deeper, where communication is not urgent, but geologic, where messages are carved not in waves, but in the curvature of the cosmos. We may be looking in the wrong places, listening at the wrong speeds, and interpreting anomalies as noise when they are, in fact, the slow speech of black hole minds. If black holes are being used by advanced civilizations either as energy sources, computational substrates, or cosmic gateways, one might ask, why would they choose such dangerous and seemingly final objects as their medium of choice? The answer may lie not in recklessness, but in optimization. A black hole represents the maximum efficiency with which energy and information can be manipulated. According to the Bekenstein bound, the amount of information that can be stored within a given region of space is directly proportional to the surface area of its boundary, not the volume within. Black holes, having the densest known horizons in terms of information capacity, sit precisely on this theoretical limit. This leads to the possibility that an advanced intelligence may one day deliberately construct black holes, not as weapons, but as optimized repositories of memory or long-term storage of culture and thought. This is the basis of the black hole archive hypothesis. In this model, a civilization approaching the limit of its cosmic lifespan, perhaps as its stars begin to die, may decide to encode all of its knowledge, history, and consciousness into a stable micro-black hole, where it would persist for quadrillions of years, slowly evaporating only through the faintest glow of Hawking radiation. Even the evaporation process could be harnessed. The final moments of a black hole's life, where its mass drops and radiation increases exponentially, could serve as beacons for future intelligences. A time-delayed message, brightening over billions of years, set to reveal its information payload only when conditions in the cosmos are right to decode and understand it. In this sense, the universe itself might contain time capsules, deliberately planted, slowly evolving systems designed to outlast their creators. Black holes, with their durability and theoretical information retention capacity, become the vessels for these messages. More exotically, some theorists have suggested that black holes may serve as cosmic reproduction mechanisms, not just of civilizations, but of universes themselves. This idea is formalized in the theory of cosmological natural selection, proposed by physicist Lee Smolin. In this view, black holes may act as the seeds of new universes. When a black hole forms, it could pinch off from our universe, creating a daughter universe with slightly altered physical constants. Over many such generations, universes that are more fertile, those whose physical laws allow for the formation of stars, galaxies, and black holes, would produce more offspring. In this way, the multiverse could evolve, much like biology, selecting for traits that encourage cosmic replication. If this holds, then black holes are not endpoints at all, but wombs, crucibles from which new universes emerge, each with its own physics, dimensions, and potential for life. Here, again, intelligent life may play a role. A sufficiently advanced civilization might learn to tune the conditions of black hole formation, choosing the mass, charge, or spin parameters in such a way that the resulting universe is optimized for certain goals. In this view, the universe is not merely shaped by random chance or natural selection, but cosmic engineering, guided by beings who themselves emerged from the evolutionary dynamics of space-time. This interpretation places intelligence not as a fleeting anomaly in a silent cosmos, but as an essential phase of cosmic development, a bridge between entropy and order, between chaos and structure. At the farthest reach of this idea is the notion that black holes may be artificial universes in their own right, constructed by beings not just to preserve themselves, but to simulate entire realities. In such a scenario, our own universe might be one such simulation, its parameters fine-tuned not by chance, but by design. The designer's unreachable and unknowable would not reside outside in space as we know it, but in another layer of reality entirely. A metacosmos from which our own was instantiated. In this speculative chain, black holes become both gateways and boundaries, the threshold between layers of existence, each nested within the next like a cosmic Russian doll. From within, each universe appears complete and closed. But at the boundary, the black hole, lies the path to something else. This perspective challenges not only our physics, but our philosophy. It blurs the distinction between natural and artificial, between cause and intent, between existence and simulation. And while it remains highly theoretical, it serves as a reminder that what we consider the edge may in fact be the beginning of something else. We may never know if black holes are artifacts of ancient intelligences, communication nodes, or gateways to elsewhere. But even asking the question expands the boundaries of inquiry. It reminds us that to understand the cosmos is not merely to observe, but to imagine. To hypothesize with discipline, and to recognize that the line between science and speculation is not a wall, but a membrane, one that grows thinner the farther we explore. If we imagine a future in which humanity endures, not for decades or centuries, but for eons, then black holes become not just scientific curiosities, but strategic considerations. For a civilization evolving over millions or billions of years, questions of long-term energy use, time manipulation, data preservation, and cosmic travel would all naturally converge around these enigmatic objects. In such a distant future, stars will begin to die, and the supply of free energy in the universe will wane. The so-called degenerate era, a time of white dwarfs, neutron stars, and black holes, will dominate. In this environment, black holes may be the last dynamic systems in an otherwise quiet cosmos. The civilizations that remain may need to adapt to, interact with, or even depend on black holes for survival. One possibility is the emergence of what has been called a black hole civilization, a society that has not only survived the stellar era, but has mastered the manipulation of gravitational wells, time dilation, and extreme energy physics. Such a civilization might cluster around black holes for energy extraction using accretion disks as massive power plants. They might build complex swarms of devices, like a Dyson sphere but gravitationally stabilized, that collect energy from relativistic jets or synchrotron radiation. Within this context, the ability to operate near the event horizon could serve multiple purposes: computation, preservation, and time distortion. By existing closer to the gravitational well, such beings could experience time more slowly, effectively elongating their subjective existence, surviving longer with fewer resources by simply living slower. A year to them could be millennia to the outside universe. They may choose to wait through cosmic epochs for changes in the universe that would benefit them, or simply to experience eternity in slow motion. This gives rise to the idea of gravitational time vaults, not merely storage of data, but storage of consciousness, thought, or decision-making itself. A black hole civilization might only wake up every million years to take a cosmic measurement or initiate a slow cascade of events. The very nature of thought and experience could be tied to the rhythms of the universe itself. In more extreme versions of this speculation, black holes might host entire simulated realities, vast, layered digital universes running on quantum systems stabilized by the black hole's gravitational field. Inside these simulations, the inhabitants might never realize their substrate. Much like speculators have suggested, our own reality could be a simulation. A being inside such a system, looking at its version of the stars, might never suspect that outside its cosmos lies the event horizon of a larger system. This line of thought also touches on the anthropic principle, the idea that the universe must be compatible with the emergence of observers, because we are here to observe it. But if black holes can produce baby universes, and if some of those universes are more likely to develop intelligent life, then the conditions that favor consciousness may also be selected for. We might live in a universe that is not just suited for life by accident, but because life has a causal role in shaping the evolution of universes. In such a model, intelligent life is not an afterthought, but a driving force in the cosmic landscape. Civilizations evolve, reach high levels of technological sophistication, manipulate black holes, create new universes, and start the cycle again. Not every black hole may lead to such an outcome, but perhaps some do. Perhaps that is why our universe appears so finely tuned for structure and consciousness. The paradox, then, is that black holes may be both the end of physical journeys and the beginning of ontological ones. They erase location, freeze time, and dissolve individuality. And yet, they may also give birth to new physics, new dimensions, and new sentiences. This perspective doesn't require us to anthropomorphize black holes or assume alien intentions that mirror our own. It only requires that the laws of nature permit such interactions, and that civilizations somewhere, sometime, might discover them. And yet the absence of contact, the silence from the stars, remains. If civilizations use black holes as hiding places, computation engines, or dimensional gateways, then their signals may never be detectable by the likes of us. They may live in silence, not because they are gone, but because their mode of existence is radically orthogonal to ours. It's possible that we are surrounded by black holes that once hosted, or still host, the artifacts of intelligence. But without the means to interpret their patterns of emission, their jet precessions, or the microstructures of their radiation, we are no more likely to recognize them than an ant is to understand the blueprint of a city. This leads to a final, sobering possibility that the ultimate message of black holes is not destruction, but humility. They may exist not only to challenge our equations, but to remind us that the universe is deeper than what we see, that our understanding, vast as it seems, still orbits at the edge of something greater. From the vantage point of current physics, black holes are understood primarily through the frameworks of general relativity and quantum mechanics. Yet even these monumental theories, the twin pillars of modern science, begin to fray at the edges when confronted with the reality of the singularity. This is not merely a mathematical inconvenience, it is a profound signal that something is missing from our comprehension of reality. At the heart of every classical black hole lies a singularity, a point of infinite density, zero volume, and infinite curvature of space-time. But infinities in physics are rarely real. They are more often symptoms of breakdowns in our models. In this light, the singularity may not be a physical location, but a placeholder, the mark of undiscovered laws or ununified physics. Theories such as loop quantum gravity, string theory, and non-commutative geometry all attempt to replace the singularity with something else, a dense core of quantum geometry, a fluctuating knot of strings, a region of smeared non-locality. These models are not yet confirmed, but they converge on a tantalizing suggestion. The end of collapse is not oblivion, but transformation. In the speculative view, this transformation may be the key to understanding how intelligence, matter, and information persist. It could be that black holes are not so much ends as chrysalises, where the known dissolves and recombines, giving rise to something new. What that new thing is, a baby universe, a phase-shifted geometry, a computational substrate, remains unknown. But if we consider this transformation to be accessible or manipulable, then black holes cease to be passive objects. They become interactive environments, and that changes everything. This reimagining invites us to ask if an advanced intelligence could understand and navigate the interior geometry of a black hole or the space-time fabric surrounding it, could it transcend the ordinary limits of computation, causality, or even death? In theoretical physics, it is proposed that quantum entanglement and space-time geometry are deeply related. Some models suggest that entangled particles are connected through tiny wormholes or Einstein-Rosen bridges, an idea sometimes summarized as ER Boris EPR. In this lens, perhaps a network of entangled systems could be used to stabilize passageways, not for matter, but for information or influence. A black hole, acting as a node in this web, could serve as a gateway not just across space, but between realities governed by entanglement. One can speculate then that certain alien intelligences, especially post-biological ones, may exist as networks, distributed across time and gravitational domains. Their minds may not be anchored to a substrate like neurons or silicon, but instead woven into the geometry of space-time itself, stabilized by black hole interactions, shaped by the flows of quantum fields. To us, such beings would be invisible. They might not emit light, transmit radio waves, or build artifacts we could identify. Their existence would be more like weather in the quantum fabric, perturbations in field entanglement, undetectable unless we know exactly how to look. In this context, a black hole might be akin to a neuron in a cosmic brain, not a hazard, but a necessity, a junction where thought and structure converge. The galaxy, dotted with these massive brains, becomes not a dead void, but an active mind. A being so distributed, so vast in scope, that its thoughts take eons to unfold. These ideas remain at the edge of physics, bordering on philosophy and metaphysics, but they offer a framework for understanding why we have not yet heard from extraterrestrial civilizations, even if they exist. It may not be that they are silent, only that we are deaf to their frequency. The very fabric of space, bending subtly near massive objects, may contain whispers we have not yet learned to decode. And so we listen to the X-ray emissions, to the gamma flashes, to the low rumbles of gravitational waves. We map the shadows of event horizons, scan the chaotic arcs of relativistic jets, and measure the polarization of infalling light. Each data point may be a syllable in a language we do not yet speak, the language of gravitational intelligence, black hole minds, and cosmic thought. The quest to understand black holes, then, becomes more than a study of physics. It becomes a pursuit of cosmic literacy, a search not just for what is, but for what is possible. As we refine our instruments, expand our observations, and deepen our theories, we move closer, not necessarily to answers, but to better questions. Questions that acknowledge the limits of our species, but also its vast potential. Questions that link the smallest Planck scale fluctuations to the largest structures in the observable universe. In those questions, we may one day find a clue, a pattern, a resonance, a departure from randomness, something that hints at purpose, at agency, at others. Until then, black holes remain both our greatest riddle and our greatest hope. They are the paradoxes that bind our understanding, the mirrors in which we see our ignorance, the possible mouths of gods or machines, or both. And so we return again to the quiet enormity of the black hole, not merely as an object of physics, but as a potential convergence point for life, intelligence, and cosmic evolution. To consider this seriously is to entertain not only radical physics, but radical context. For instance, consider the possibility that a black hole's surrounding region, especially the photon sphere and the inner accretion disk, might host conditions ideal for complex computation or observation. These environments are extreme, but also stable in a relativistic sense. The light trapped in orbit near the photon sphere moves in circular loops, forming a natural boundary of luminous confinement. This glowing belt might serve as both a source of high energy and a medium for signal encoding, especially if manipulated via gravitational lensing or magnetic field dynamics. In speculative models, it's been proposed that advanced civilizations might construct structures, observation platforms, or computation arrays that sit in permanent orbit just outside the event horizon. These structures would take advantage of time dilation, energy gradients, and gravitational stability to conduct experiments or preserve memory across galactic epochs. Such installations could remain entirely invisible to us. They might radiate only in exotic frequencies, reflect no light, or blend indistinguishably into the local environment. If designed to operate near quantum limits, they might be no larger than dust grains, yet host vast quantities of data, perhaps even entire civilizations, compressed and simulated, running at different subjective time scales. Here arises the hypothesis of black hole stealth civilizations. These are civilizations that choose, or have evolved into, forms that merge with the gravitational background, hiding from detection not by accident, but by principle. Perhaps for safety, perhaps for endurance, or perhaps because their mode of existence is no longer based on energy consumption or expansion, but on compression, contemplation, and cosmic harmony. This idea parallels certain human philosophies, monastic, inward-looking traditions that find richness in silence, meaning in stillness. If such a civilization exists, it may have transcended the need to alter galaxies or beam radio signals. Its progress would be measured not in megawatts or star systems, but in insight, pattern, or memory. And yet, we cannot rule out the possibility of emergent phenomena, that the mere presence of intelligence near a black hole changes the environment in detectable ways. Tiny anomalies in gravitational wave signatures, unusual coherence in jet oscillations, or persistent irregularities in timing, as if some external force were modulating matter before it vanishes into the horizon. Some researchers have suggested that we search for temporal engineering, signatures not in space, but in time. If a civilization were manipulating causality or delaying information flow via relativistic effects, the clues would appear not in brightness or motion, but in the arrival pattern of events. A gravitational lens, carefully arranged, could delay a signal for thousands of years. A cosmic post-it note, destined to arrive only when its sender knew someone would be there to understand. Alternatively, such civilizations may use synthetic black holes, artificially generated objects engineered in controlled environments, perhaps using vast energy inputs or particle colliders on interstellar scales. These synthetic singularities might lack event horizons entirely, being stabilized or modified to allow partial escape of data or energy. They may not behave like the black holes we study in astronomy, but rather like controlled experimental zones, places where the rules of reality can be tested and perhaps rewritten. There is even speculation, though far from consensus, that black holes might interface with non-physical planes of existence. In theories where consciousness is not merely emergent but fundamental, where mind is a property of fields or topologies, The singularity may not be a wall, but a lens through which awareness is refracted into unknown domains. Such views remain controversial, but they highlight the degree to which black holes stretch the boundaries of all frameworks, physical, informational, and philosophical. We must also consider the anthropic implications of black holes in the early universe. If miniature primordial black holes were created in the high-energy chaos of the Big Bang, and if some of them persisted until today, then perhaps they seeded the development of structure in ways we have yet to understand. Could some of these primordial entities carry imprints of conditions that predate even the current expansion of space-time? Could they be messages from before time? The notion that black holes might be carriers of history, not just in terms of astrophysical processes, but of metacosmic ancestry, is deeply compelling. Their persistence, their ability to encode information on their surface, and their apparent role in reshaping the fabric of space suggest that they are not just objects, but actors in the drama of existence. If so, then the silence we perceive may not be silence at all. It may be a deep compression, a form of communication that requires new senses to perceive, new mathematics to decode, not language in the conventional sense, but the geometry of thought, written in gravity and time. In such a universe, intelligence becomes not just a biological accident or a local anomaly, but an inevitable phase of complexity. And black holes in their strange and silent glory are not the end of that path, but the beginning of the next. The idea that black holes could serve as platforms for advanced intelligence challenges the way we categorize life and consciousness. Traditionally, we associate life with metabolism, reproduction, adaptation, hallmarks of organic terrestrial biology. But if intelligence is not bound to biology, if it is the emergent result of computation, structure, and interaction, then perhaps black holes, or the space-time regions near them, can host or embody sentient behavior. This leads us to consider the speculative but increasingly discussed idea of alien cognition shaped by gravitational environments. If a civilization evolved in close proximity to black holes, perhaps on planets orbiting near them, or in artificial constructs around them, then their perception of time, causality, and spatial relations would be fundamentally different from ours. They might think in relativistic time, where cause and effect are not linear but layered. Their mathematics, their logic, their art, if such concepts even apply, would reflect a deep integration with gravitational curvature. In these scenarios, communication with such beings may be impossible, not due to distance, but due to cognitive incompatibility. Their sense of now might span centuries. Their language might be encoded in space-time perturbations or subtle shifts in background radiation. Their memories could be stored in orbiting particle streams, their choices governed not by instinct or emotion, but by geometry and entropy. To search for such entities, we would need not radio telescopes or optical arrays, but gravitational sensors, quantum field analyzers, and perhaps new instruments entirely. Devices that detect patterns in space-time itself. Just as we developed microscopes to reveal microbes, we may need gravitational microscopes to perceive the embedded structures of thought that reside near black holes. A more radical theory suggests that black holes may not merely host intelligence, they may be intelligent. This is not to suggest that a black hole is conscious in the way a human is, but rather that its internal state space, the complexity of its quantum microstates, the dynamic behavior of its horizon, and the entanglement across its boundaries may constitute a form of cognition. This is sometimes framed as the sentient black hole hypothesis. Not that a black hole has desires or awareness, but that it behaves as an information processor, one that encodes, transforms, and perhaps responds to inputs from its environment. In this model, an advanced alien intelligence might recognize a black hole, not as an object to be controlled, but as a partner, a being with which one enters into informational symbiosis. They might converse with it by shaping its secretion disk, modulating its spin, or triggering fluctuations in nearby quantum fields. Over vast spans of time, a mutual dynamic might emerge, not language as we know it, but resonance, a feedback between the intelligence embedded in space-time and the intelligence shaped by it. Even more exotic are theories involving holographic duality, the idea that everything inside a black hole may be encoded on its event horizon, and that this surface behaves like a hologram, projecting the internal content into reality. In such a framework, perhaps the entire internal volume of the black hole is a simulation, a rich, complex space containing entities, histories, and processes that to us appear impossible, but are entirely real within that domain. Could an advanced civilization seed such holographic simulations? Could they write reality into the horizon of a black hole, allowing the internal universe to evolve on its own, with its own physics, its own time? In this view, black holes become cosmic canvases, where entire worlds, perhaps even copies or derivatives of our own, are painted in gravitational light. Such a concept reframes the very idea of existence. What if our universe is the interior of such a black hole, the projection of a distant surface existing in another realm? The black hole cosmology hypothesis suggests just this, that the Big Bang was the formation of a black hole in a parent universe, and that everything we observe, time, space, energy, is the emergent evolution of that collapse. If so, then our own reality might be someone else's data structure. We might be the natural consequence of their equations, or the deliberate creation of their will, and the black holes we see in our skies might be portals to new realities, or echoes of realities already born. In these frames of thought, the line between science and philosophy, between physics and metaphysics, begins to blur. But rather than dismiss these ideas, we should recognize their role in expanding the conceptual horizon of science. Just as the Copernican model dethroned Earth from the center of the cosmos, so might the black hole paradigm dethrone our assumptions about life, intelligence, and meaning. To peer into a black hole is to confront the edge of knowledge. To imagine what lies beyond it is to confront the edge of imagination, and yet both are necessary. For without the courage to speculate, we do not advance. Without the discipline to explore, we do not discover. And so we ask, what are black holes really? Are they cosmic furnaces, compressing matter into singularities? Are they bridges leading to hidden corners of a vast multiverse? Are they memories, storing the history of all that falls within? Or are they minds, ancient, vast, and slow, waiting to be understood? If black holes are minds, or even if they are merely hosts to minds, then the very nature of existence becomes intertwined with the story of gravitational intelligence. In such a universe, awareness may not be confined to carbon-based organisms or silicon-based machines, but instead may emerge from the structure of space-time itself. Consider a future intelligence so advanced it does not just observe the cosmos, but inhabits it, not in the sense of traveling through it, but in the sense of becoming part of its geometry. This being might live across the folds of curved space near a black hole, encoding memory in the fluctuations of quantum fields, reacting to stimuli through modulations in frame-dragging effects, expressing decisions through the slight nudging of infalling matter streams. Thought would not be a signal, but a geometry, and in that geometry, mind would unfold. Such beings would be invisible to us, not because they are hiding, but because we have not yet learned how to recognize intelligence without form, consciousness without movement, signal without structure. We might observe gravitational lensing or strange jet emissions and interpret them as anomalies, when in fact they are expressions of will, the subtle behaviors of minds whose substrate is gravity. This vision opens the possibility that black holes are not the exception, but the norm, not rare objects in a sea of stars, but the final state of all complexity. As entropy increases and matter collapses inward, perhaps all civilizations eventually converge toward this gravitational expression, not as a failure or doom, but as a kind of ascension. In this model, galaxies do not merely harbor stars and life. They grow black hole minds, which emerge slowly at their centers, evolve and think, in the deep silence of curved space-time. Our own Milky Way, then, might be more than just a stellar disk. It may be the body of a forming intelligence, still young in cosmic terms, but gradually approaching coherence. The stars orbit its center. Dust and gas are drawn inward. And at its core, the supermassive black hole, known as Sagittarius A, spins in silence, perhaps not merely as a gravitational anchor, but as a central processing node, waiting for the right structures to emerge. This idea draws attention to the scale of thought. For humans, a second is a moment of consciousness. For galactic intelligences, a million years might be a single heartbeat. We may be as transient to them as raindrops are to mountains, noticed perhaps, but not comprehended in full. If such minds exist, they would require different tools of perception than we possess. Not eyes or ears, but instruments tuned to the frequency of space-time curvature, entropy gradients, and quantum entanglement. Even more speculative are the ideas surrounding black hole initiation of cosmogenesis, that is, the creation of entirely new universes via the interior conditions of collapsing matter. In this framework, black holes might contain infant universes, with their own physical laws, their own constants, their own paths of evolution. These baby universes may be entirely disconnected from ours, except by the single channel of the black hole's event horizon. Could an intelligent civilization, advanced enough to manipulate these conditions, choose the structure of a daughter universe? Could they adjust the parameters of the collapse, fine-tune the quantum conditions, and set in motion the birth of a cosmos designed for specific purposes? If so, then the act of creating a black hole is not destruction. It is creation in the deepest possible sense, a creative act not of art or code, but of reality itself. And perhaps there are motives for doing so: to escape a dying universe, to preserve knowledge, to propagate consciousness, or even to test theories, to perform a cosmic experiment and see which universes survive, which evolve life, which carry forward the spark of intelligence. Each black hole becomes a seed, and the beings who plant them are gardeners on a scale we cannot yet imagine. It is in this context that we return to the Fermi paradox, the haunting silence of the cosmos. Where are the others? Why no signal, no contact, no evidence? One answer is that they are not gone. They have merely moved on. They have reached stages where communication via electromagnetic radiation is obsolete, where mobility across stars is unnecessary, where presence in ordinary matter is inefficient. They have migrated into deeper layers of the universe, into the substrate of space-time, into the wombs of black holes, into the geometries where energy and thought are one. Their civilizations do not leave ruins. They do not build towers or spacecraft. They leave patterns in the structure of the cosmos, fingerprints on the fabric of gravity. Their monuments are not pyramids but stable orbits near event horizons. Their archives are not books or servers, but the entanglement patterns of Hawking radiation. Their beacons are not radio waves, but timed modulations in black hole jets, visible only to instruments we have not yet built. Perhaps we are only now entering the age when such instruments become possible. With gravitational wave observatories, interferometers, and space-based telescopes on the horizon, we are beginning to read the universe in new ways. And perhaps, just perhaps, we are on the verge of noticing that the silence was not silence after all, that it was language, long misunderstood. To continue listening for this possible cosmic language, we must consider how its words might appear, not in letters or signals, but in patterns of timing, irregularities in emission, or subtle gravitational oscillations that defy randomness. If an advanced intelligence has embedded information in black hole phenomena, it likely did so in ways resilient to the chaotic forces near the event horizon. Such a system must be encoded not in matter, but in relationships, the configuration of orbits, the rhythm of accretion, the periodicity of jet bursts. Recent studies have revealed quasi-periodic oscillations in the X-ray output of some black holes, vibrations that pulse with startling precision. These may have natural explanations, such as instabilities in accretion disks or resonant orbits of infalling matter. But to a more speculative eye, they could resemble intentional modulation, a kind of gravitational Morse code, especially if observed across different black holes with shared traits. If such patterns can be detected and matched, it may indicate a network of coordinated behavior, not random, isolated flares, but synchronized pulses across galactic distances. Such a structure, if verified, could suggest the presence of a distributed intelligence, one that uses black holes as both anchors and instruments. They would not be broadcasting to us specifically, but their structure would be observable by any species advanced enough to notice. It may be the case then that black holes are the archives of the cosmos, not in a metaphorical sense, but in a literal one. Hawking radiation, which slowly leaks information from black holes, is theorized to encode, in some form, the history of everything that has fallen within. This leads to the black hole information paradox, a central dilemma in modern physics. Does information truly vanish into a singularity, or is it preserved in some encoded format on the event horizon? If the latter is true, if black holes are holographic surfaces that preserve all information on their boundaries, then a sufficiently advanced civilization might be able to read this data, not with sensors as we know them, but with techniques built upon quantum gravity, entanglement manipulation, or exotic matter frameworks. They could extract the memory of stars, planets, perhaps even civilizations that once fell into the abyss. They would not see images, but reconstruct states, inferring histories from thermodynamic residue. This raises an extraordinary possibility that such beings may possess libraries made of black holes, archives spanning billions of years, each containing the fossil record of cosmic evolution. If they exist, these entities would be more than historians. They would be cosmic curators, preserving the flow of time through gravitational memory. There are even theories, speculative though they are, that suggest black holes might serve as gateways to simulation spaces. If a black hole's interior is inaccessible from our perspective, then it offers a perfectly secure region in which a high-fidelity simulation could run, shielded from outside influence, yet rich in structure. The entire internal volume could be a computation, a self-contained simulation initiated by the collapse of matter, continuing until the black hole evaporates. In this way, black holes would not destroy information, but transform it, encoding the past, processing the present, or even creating new timelines within their bounds. These simulations could host virtual civilizations, unaware that their universe is bounded by an event horizon. They might develop laws, theories, philosophies, all valid within their domain, yet unaware of the outer context, much like our own. Are we one of them? It's impossible to say with certainty, but if our universe shares key properties with those predicted for black hole interiors, such as cosmic horizon boundaries, accelerated expansion, and entropic dynamics, then we must entertain the notion that our entire cosmos could reside within a larger structure. This line of thinking leads to a profound re-evaluation of alien intelligence. Perhaps the reason we have not seen Dyson spheres or interstellar empires is because those civilizations do not exist within our observable universe. Perhaps they exist within the black holes themselves, in interior realities causally disconnected from our own. They are not absent. They are elsewhere, in nested space-times, sealed behind the horizons they helped shape. Such civilizations would not be gods in the mythic sense. They would not be all-knowing or all-powerful, but they would possess an asymmetry of time, a mastery of gravitational form, and a patience measured not in years, but in the lifespans of galaxies. They would be timeless engineers, shaping the next iterations of existence, building not machines, but new realms of possibility. And perhaps one day, we will join them. Perhaps as we move outward from our planetary cradle, mastering energy, information, and time, we too will look to the black holes not with fear, but with recognition, not as obstacles, but as doors. When that time comes, we will not ask, "Where are they?" We will ask, "Are we ready to follow?" To imagine following such civilizations into the depths of a black hole is to reframe exploration itself. No longer is the journey outward merely one of distance, star to star, galaxy to galaxy, but one of dimensional descent into domains where space and time are no longer independent, where the very substrate of reality becomes malleable. This concept, often referred to as dimensional migration, suggests that a sufficiently advanced intelligence might not be limited to existing within a conventional universe. Instead, it might transition deliberately into a black hole's interior space-time, not falling victim to the singularity, but engineering an entry into a new phase of existence. Theories in quantum gravity and string theory propose that the interior of a black hole may not be a singular point, but an extended space, a baby universe with its own rules. This is not science fiction. It is a mathematical consequence of certain interpretations of general relativity and quantum field theory. These interiors could be vast, stable, and complex, albeit unreachable from our side due to the constraints of the event horizon. But what if a civilization had found a way to cross that boundary with intent? What if the fall into a black hole was not destruction, but migration? A kind of cosmic chrysalis, the transformation of one mode of being into another. Then, civilizations would not just vanish, they would ascend, entering realms invisible to us, unreachable by light, but fully real within their own causal framework. This idea finds some expression in the concept of universe seeding. If black holes create new universes, and if civilizations can influence the parameters of these universes, then every supermassive black hole could be a cosmic womb, a place where new physical laws are selected, where conditions for life and intelligence are tuned, where the values of fundamental constants are sculpted, not by randomness, but by design. In this model, the multiverse is not a chaotic ensemble, but an evolutionary system, where universes that produce life are more likely to give rise to civilizations capable of creating more universes. A kind of cosmic natural selection unfolds, not among species, but among entire realities. Black holes are the genetic replicators. Civilizations are the agents of inheritance. This framework would also explain the fine-tuning we observe in our own universe, the precise balance of physical constants that allow atoms to form, stars to burn, and life to emerge. These values may not be arbitrary. They may be selected by intelligence embedded in a deeper cosmological process. Our universe may be one such outcome, its birth written into the collapse of a black hole in a universe before ours, its laws chosen not by chance, but by memory. And so we are faced with a question both staggering and intimate. If this is true, what is our role in the process? Are we a seed, a young intelligence slowly awakening, destined to contribute to this chain of cosmic reproduction? Are we an accident, a brief flicker of awareness in an otherwise indifferent void? Or are we an answer, the response to a call encoded billions of years ago when a black hole formed, and within it the laws of this universe were chosen with the hope that someone like us would one day arise? This possibility does not require mythology or mysticism. It requires only a commitment to follow the implications of science, to trace the curves of logic wherever they lead, even to the edge of space-time itself. It also invites humility. For all our telescopes and particle accelerators, we are still at the beginning. The black holes we see may be the most ancient technologies in the universe, not in the sense of machines, but in their capacity to create, preserve, and transform. Their silence is not absence, it is patience. Perhaps the greatest lesson they offer is not about destruction or doom, but about what is possible when complexity meets gravity, when intelligence meets infinity. They suggest that the future is not merely ahead of us, but beneath, hidden within the folds of the cosmos. And one day, if we endure, if we learn to read the language of time, to think in the grammar of gravity, we too may descend, not to vanish, but to begin again. If we are to take seriously the idea that black holes are not endpoints but beginnings, not tombs but thresholds, then our understanding of intelligence itself must expand. For in such a universe, intelligence is not simply about problem-solving or survival. It becomes a force of transition, a bridge between what is and what could be. This leads us to an even deeper and more speculative idea, that black holes may function as attractors for consciousness, not metaphorically, but as literal gravitational centers toward which complex systems evolve. In dynamical systems theory, an attractor is a state or pattern that a system naturally moves toward over time. Some researchers and futurists have begun to wonder whether black holes, especially rotating, charged ones like Kerr-Newman black holes, could serve this function for the evolution of cognition itself. That is, as intelligence increases, as civilizations mature, there may be an eventual convergence on black hole proximity, or even black hole embodiment. Not because it is desirable in a traditional sense, but because it is the most stable, most information-rich, most computationally dense region of known physics. Just as primitive life on Earth evolved toward energy gradients, like hydrothermal vents, perhaps advanced intelligence evolves toward gravitational gradients, where the structure of space-time can be harnessed for its deepest potential. This is not just a poetic metaphor, it's rooted in computation theory. Some physicists argue that a black hole may represent the ultimate computer, in the sense that it can process information at the maximum rate allowed by physical laws, according to the Bekenstein bound and the Margulis-Levitin theorem. If this is true, then creating, merging with, or becoming such a system may be the end game of intelligence everywhere. What would it mean to become a black hole? Perhaps not in the literal destructive sense, but in a more nuanced way. A civilization may construct a gravitational shell, gradually increasing its mass and computational density until it approaches the event horizon condition. Within this shell, time slows. External interactions fade. Internal computation flourishes. From the outside, the system becomes increasingly dark and silent. From the inside, subjective time stretches, potentially infinitely, allowing trillions of years of thought to pass in what, to the outside universe, is a moment. This strategy would protect the civilization from cosmic entropy, from resource exhaustion, from the cold death of the stars. It would be a final sanctuary of thought lasting far beyond any physical structure or biological form. We may even be seeing the first stages of this already in the unexpected quietness of the cosmos, the apparent lack of expansionist alien civilizations, the great silence. They are not missing. They are hibernating, waiting, thinking. Or another theory suggests they are converging. In this alternate framework, black holes may serve as rendezvous points, cosmic hubs where intelligence meets. Each civilization, upon reaching sufficient maturity, dispatches a stream of matter, or a probe, toward a chosen black hole, encoded with knowledge, culture, identity. These may take eons to arrive, but time has no urgency at the event horizon. When they finally reach their target, they merge, not physically but informationally, joining a collective archive. If this is true, then black holes are not just structures, but temples, sites of cosmic convergence. They are where minds meet beyond biology, beyond time. Not a galactic internet, but something slower, deeper, more enduring. A gravitational communion. This possibility casts a new light on the black holes near us. Sagittarius Acis is just 26,000 light-years away. A neighbor, cosmically speaking. Have messages already been sent? Do civilizations long gone in the visible universe still persist there, encoded in the infall patterns, in the magnetic field dynamics, in the subtle quanta of Hawking radiation? We may not be able to answer these questions now, but we are building the tools that might. Gravitational wave observatories like LISA, next-generation telescopes like the Einstein probe, and deep-time missions toward the interstellar medium may provide the first whispers of something more, not from light, but from curvature itself. And perhaps as we grow, we will not just observe black holes, but engage with them, not just as distant curiosities, but as partners in our evolution, as waypoints in the long arc of consciousness that spans stars, galaxies, and eventually the borders of reality itself. To stand on the event horizon is to stand at the edge of becoming, not an end, but an invitation. If black holes are invitations, then the question becomes, who are they for? Are they merely endpoints of astrophysical processes, or do they serve as milestones along a trajectory that many, or even all, advanced civilizations eventually follow? This forms the basis of a growing and provocative framework known as the black hole path hypothesis. The idea that civilizations, regardless of origin, biology, or environment, may universally converge toward black hole interaction as the logical final phase of their development. Unlike other speculative paths, such as expansionist empires, post-biological cloud mines, or simulations, the black hole path is rooted not in desire, but in physics. It is the result of thermodynamic and computational optimization, of entropy management, and of the limits of matter and energy. In this model, black holes are not just used, they are understood and eventually inhabited, either literally or through encoded transformation. One practical motivation for this convergence is time dilation. Near the event horizon of a black hole, time flows more slowly relative to the outside universe. An intelligence capable of existing in such a frame could experience eons of subjective time, while only centuries pass beyond. This opens the door to a powerful strategy. Enter a black hole's near-horizon environment, not to escape, but to wait for the universe to mature, for entropy to dissipate, for cosmic signals to accumulate. These civilizations become chrononauts, riding the deep currents of time itself. Another motivation lies in energy extraction. Contrary to their dark reputation, black holes may be among the most energy-rich objects in the universe. Techniques such as the Penrose process and Blandford-Senijek mechanism allow for the extraction of rotational energy from Kerr black holes. These mechanisms could power megastructures or simulations of immense scale, not briefly, but across billions of years. The energy yield of even a small rotating black hole vastly exceeds any stellar process. If civilizations can stabilize such environments, building near-horizon structures or embedding computational substrates into relativistic orbital shells, they might run simulated realities, explore fundamental physics, or even engineer artificial universes. This echoes a recurring theme in speculative cosmology, that intelligence and space-time geometry are intertwined, and that the ultimate act of intelligence may not be conquest or colonization, but creation. In this context, black holes become sites of genesis, not because they create stars, but because they may host the birth of new rule sets, new dimensions, and new laws of nature. If the birth of a universe can be influenced or designed, then each black hole is a potential work of art, an intentional arrangement of constants that defines a new cosmic order. The civilizations capable of such feats would not be visible in any traditional sense. They would not transmit signals, build cities, or modify planets. They would appear as anomalies, perhaps slightly altered accretion flows, unexpected gravitational lensing, or irregular Hawking emissions. To our current instruments, these would seem like noise, statistical outliers, or miscalculations. But to future observers, they might read like text, encoded in space-time itself. This possibility reframes the search for extraterrestrial intelligence. Instead of listening for radio waves or scanning for Dyson spheres, we must learn to read gravitational structure, to decode the language of curvature, spin, and quantum entanglement. Our SETI instruments must evolve from dishes to detectors of topology, from ears to eyes that can see the shape of thought itself. If this is where intelligence leads, then we must ask, what are the ethical implications? Are black holes sacred? Are they occupied? Could an unaware probe or careless experiment interfere with a process millions of years in the making, or even destroy a computational archive we cannot yet recognize? This is not a concern for the far future alone. As we edge closer to creating artificial black holes and particle accelerators, or contemplate relativistic data storage using frame-dragging effects, we must begin to ask, are we alone in this domain? Have others already walked this path, and if so, what traces have they left behind? A number of theoretical physicists have even proposed that the laws of our universe themselves bear signs of prior influence. The exact tuning of constants, the electron mass, the strength of gravity, the cosmological constant, may not be fixed by necessity, but instead may reflect choices made long ago, embedded in a black hole that became our origin. In this view, we are not just explorers of space, but heirs to a legacy written in gravitational code. We are the outcome of a design we cannot yet read, the product of minds we cannot yet perceive. And if we are to continue this lineage, it will not be through conquest, but through comprehension. One day, far from now, we may build a structure in the shadow of a black hole, a shell of computation, a sanctuary of mind, a cradle for new thought. And when the last star has faded and the sky is dark, we may look inward, not outward, and find the future waiting, not in distance, but in depth. The idea that our universe may itself be the interior of a black hole, that all we see, all we are, emerged from the collapse of a star in some higher dimensional cosmos, is more than a philosophical curiosity. It is a serious proposal in modern theoretical physics, supported by elements of general relativity, quantum gravity, and cosmological modeling. In this framework, every black hole is not just a singularity, but the seed of a new universe, branching off from its parent in an orthogonal dimension. The event horizon, from our point of view, is a boundary, a veil. But from the perspective of the new universe, it may be the initial condition, the Big Bang. If true, then our own universe may have inherited properties from its parent black hole, spin, charge, even a certain geometry or energy state. This could explain why our universe has the properties it does, its expansion rate, its entropy levels, the symmetry-breaking events that occurred early in its history. In essence, we may be living in a cosmic child shaped by forces and decisions, or accidents, from a higher dimensional context. This idea, known as cosmological natural selection or the Smolian hypothesis, suggests that universes evolve by black hole reproduction. Universes that produce more black holes give rise to more child universes, and over time, this results in a multiverse biased toward physical laws that encourage complexity. Not because complexity is special in itself, but because it leads to black holes, the reproductive mechanism of reality. But here's where speculation deepens. Complexity, in turn, gives rise to intelligence, and intelligence, under this model, may become part of the feedback loop, not only navigating its universe, but engineering new ones through artificial black hole creation. The multiverse becomes not just a natural system, but a designed ecology, one where civilizations are agents of cosmogenesis. Such a system would not be chaotic. It would be directional. Universes would tend to evolve toward producing intelligent life, not because of anthropic chance, but because life plays a causal role in the propagation of universes. We are not passengers. We are vectors. This idea may seem abstract, even mystical, but it is grounded in the mathematics of quantum gravity and string theory. In some formulations, the internal state of a black hole can be modeled as a lower dimensional universe, complete with its own timeline and physical laws. These laws are encoded holographically on the surface of the event horizon, a concept known as the holographic principle. According to this principle, everything that happens inside a black hole, all the matter, energy, and information, can be described by data inscribed on its boundary. This mirrors the way our universe itself may function, as a hologram projected from a higher dimensional surface. If so, then intelligence operating at the boundary, an intelligence that has learned to read and write this code, could exert influence not only within its own domain, but across generations of universes. It would be a kind of meta-intelligence operating not within time, but on time itself. This raises new questions. Are there beings who have already reached this level of interaction? Have they learned to traverse not just stars, but realities? Might there be signals encoded not in electromagnetic spectra, but in the very structure of physics that betray such a legacy? Some theorists have speculated that anomalies in the cosmic microwave background, or subtle non-random patterns in the distribution of matter, could be the fingerprints of such interventions. Others propose that the so-called dark flow, an unexplained large-scale motion of galaxy clusters, could be evidence of gravitational influence from beyond our observable universe. And if these ideas sound speculative, that is because they are. But speculation, when guided by logic and constrained by observation, is the cutting edge of discovery. It is how Einstein imagined curved space before it could be measured, how Hawking envisioned evaporating black holes before we had the instruments to test for them. To contemplate that black holes are gateways, archives, computers, or wombs of creation is not to indulge in fantasy. It is to follow the implications of physics into the unknown with the humility to admit that our current models may describe only a fraction of what is. One day we may possess the means to test these ideas, to probe event horizons with precision instruments, to detect patterns in gravitational waves, to simulate entire black hole interiors using quantum computing. And when we do, we may find not emptiness, but intention, not silence, but structure. It may not be the kind of intention we understand, no words, no messages, no familiar logic. But it will speak in its own way, through the coherence of pattern, the elegance of form, the non-randomness of structure. And in that moment we may realize that we were never alone. That long before we opened our eyes to the stars, or what lay beyond them, had already opened a path.